Good evening, everyone. So, welcome to day 5 of our ATAL sponsored faculty development program on innovative green energy generation and storage technologies. I hope you found yesterday's sessions are very interesting and are ready for today's exciting topics. Yesterday Professor Radha Manohar Rao emphasized the importance of various advanced energy harvesters. In the second session, Dr. R. Balaji, Senior Scientist, ARCA, Chennai, discussed about the advanced technologies for green hydrogen production. So today's program includes two insightful sessions designed to inspire all of you. The first session will focus on next generation smart grid technologies. The speaker for this session is Dr. R. Van Prakash, Power Electronics Engineer, Idea Forge Technology Limited. His research areas are charger design, inverter development, solar PV applications, and grid-connected converters. Dr. Bhanu Prakash will share valuable insights into the next generation smart grid technologies. In the second session, Professor E. Anil Kumar, Department of Mechanical Engineering, Dean Sponsored Research and Consultancy, IIT Tirupati, will talk about hydrogen storage technologies. I encourage everyone to participate actively, interact with the experts, and share your thoughts during the sessions. We are delighted to welcome Dr. Bhanu Prakash, who will be sharing his valuable expertise and perspectives on next generation smart grid technologies. It is a privilege to have such a renowned expert with us to deepen our knowledge in this vital area. Before we begin, I invite our session coordinator, Dr. K. Ravikumar, to introduce today's speaker. Over to you, Dr. K. Ravikumar. Please share more about our distinguished speaker of this session. Thank you.
Okay. Thank you, sir. Thank you so much. So, good evening, everyone. It is with great pleasure that I introduce today's distinguished guest, Dr. Bhanu Prakash, sir, a certain expert in the aerospace industry with over a decade of experience in the dynamic field of power electronics. Dr. Bhanu Prakash, sir, extensive career has been defined by innovation, leadership, and commitment to advancing technology in critical areas such as charger design, inverter development, solar PV application, and grid-connected converters. Throughout his professional journey, Dr. Bhanu Prakash, sir, has been instrumental in the development of cutting-edge power electronic systems that enhance the efficiency and reliability of aerospace technology. His contributions have not only driven innovation but also set benchmark in product performance and sustainability. Dr. Bhanuprakash sir expertise extends across several vital domains including power converter design and optimization, renewable energy system integration, energy storage solutions, and power system analysis. His deep understanding of ENC and safety standards has ensured compliance with industry regulations while maintaining the high performance outcomes. As a leader in research and development, Dr. Bhanuprakash sir has successfully led cross-functional teams driving the design and deploying of high-performance solutions that meet the evolving demands of aerospace applications. His dedication to excels and his ability to stay at the forefront of emerging technology have earned him widespread widespread recognition as a trusted expert and innovator. Today we have privileged to have Dr. Bhanuprakash sir joined us for his faculty development program. His insights and expertise will inspire us and provide valuable perspectives on the transformative role of power electronics in the both academic and industry. Please join me in extend warm welcome to Dr. Bhanuprakash sir as he share his knowledge and expertise with us. Thank you, sir. You please uh, share your thoughts, sir.
Am I audible?
Yes, sir. You're audible,
Yes, sir.
but
Yes, sir.
your
Audible.
video was not enabled.
Turn it off because of internet issues.
Okay, okay.
Yeah. So, Dr. Sivasubramanian and Dr. Ravi Kumar, thanks a lot for your brief introduction about me. And thanks for giving me this opportunity to start on smart grid technologies. So I'll be presenting. Is it visible?
Yes, sir, it's visible.
So I've recently changed my company. So I'm a solar PV design engineer in News-Based Research and Technologies for aviation applications. Let's begin with the session, Next Generation Smart Grid Technologies. So the actual content that we are looking for is Introduction to Smart Grid Technologies. What is this smart grid and what are the technologies that are under it, and core technologies in the next generation that we are seeking for. What are the challenges, barriers, innovations, and emerging trends that are coming in smart grid? What are the implementation strategies and case studies? Finally, what are the upcoming trends that we have to still see, look after the smart grid? Is the slide changing happening for you? Hello?
Sir?
Is there a slide change for you?
No, sir. Can you change the slide, sir? Yes, sir. Yes, sir. Now it's changing. Sir.
Now slide is changing. Yes.
Yes, sir.
Yeah.
Yes, sir.
You please continue, sir.
So, what is the smart grid, and what are the actual electrical grids that we have, and why we need to call it as smart grid? So normally, as we know, the evolution of electrical grids, as we see the evolution of electrical grids, we just transmit power between the consumer and producers through some transmission lines. This is a conventional form of grids, but with the advent of time, what we have experienced is there are a lot of things that needs to be work smarter. For example, you have your own power generation in your household, and you still need to do whenever you want to feed the power to the grid, you can feed it, and whenever you want the power back, you can take it up. So in these two things, to make a dual bidirectional power flow, your grid should be smart enough to understand the power flow and to command or to have a regulation accordingly. So understanding the smart grid is an electricity network enabling two-way communication between suppliers and consumers to manage electricity flow efficiently. And it leverages digital technology to monitor, predict, and react to electricity usage in real time. Again, enhances the reliability, efficiency, and sustainability. These are a very key aspects. We have to make sure whatever the power that we have, it should be reliable and it should be efficient as well. I mean, the two-way communication will enhance the efficiency and it should be sustainable. So for the longer duration as well. So again, the evolution of electrical grids, as I said, traditional grids were one of the unidirectional sending power from generation sources to consumers. So there is no way that a consumer is going to give power back to the generation system. I mean, that such provisions are not there in the initial stage. Now they were evolving. So the transition includes the integration of advanced digital technology for better management, which we are going to see in the consecutive slides. So modern grids incorporate renewable energy sources and distributed energy sources. So what I mean distributed energy sources, you can have your own power generation. It can be by any means, or a separate private entity can also generate its own power. So this is distributed energy sources. So we have to incorporate all this like renewable energy and distributed energy sources into the grids. Then the evolution actually comes up. Then you have to be smart to handle all these electrical grids. The smart grid improve resiliency and response time in case of outages and disruptions. I think you heard of a term called blackout. Blackout is something because of heavy loading or some faulty system that creates burden on the entire power system, which makes the entire grid to collapse. So you have to cut off the power supply to protect the power plants. In such cases already happened in multiple countries multiple times. Even it happened in the year 2011 December in India also. Southern distributed regional regional center has experienced that. Even northern NRDC also has experienced it. So to prevent such blackouts, if your grid is smart enough to detect, then you can able to prevent such outages or disruptions. Even the smart grid will facilitate better integration of the renewable energies, reducing resilience on fossil fuels. So by renewable energies that we are going to see now, enhance energy efficiency by accurately balancing supply and demand. What are the key components of smart grids? If I consider smart grid, what is this? Smart grid technologies. So it is mainly of 4 different types. How you are metering, how the two-way communication happens. So we are going to involve, or we are going to indulge a system of advanced metering into the system. Advanced metering infrastructure allows for automated two-way communication between meters and utility companies. So what happens now? You have a meter that gives the data, that gives a real-time data to the prosumers. I mean, we are producer and we are consumer. Assume that we have power generation on our own, and we are also generating the power. We are consuming as well. By default, we are consumers. If we have some power source generation, we can give power as well. So we call prosumers. If we, as a prosumer, I need to incorporate advanced metering infrastructure so that enable me to have two-way communication between meters and utility companies, so that how much power I have consumed, at what time, what rate, what is the loading that I have been done. All these things will come under real-time data. So this real-time data collection will happen in the smart grid. What happens is it will actually indeed assist in demand response and load management. So the load is highly unpredictable. There is like short-term forecasting, long-term forecasting. There are multiple algorithms that people use, like centralized, decentralized networks. A lot of things are involved in this. So demand response. So what is the demand and how the grid is responding to that? And load management, whatever the load that we have, how we are managing. Is it, are we tripping off it? Are we stripping the load, or are we connecting the load? This is one part of the segment that usually happen. Next, distributed energies resources. Distributed energies resources include small-scale power generation sources like solar PV, wind turbines, and battery storage. It doesn't, so normally the renewable energy sources we generally call photovoltaics, wind, fuel cells, a lot of other things. But these are the 3 major dominant segments that we involve, like solar PV panels, like most of the households are being adopted. And in some of the remote areas, we install solar PV plants and wind turbines for the power generation based on the location. And battery storage, if you have an independent house and you're having for reliable power, you generally have UPS or inverter battery storage based UPS. So these are the major things that comes under distributed energy resources. What is this advantage? Now, promote localized energy production. Now I am producing my own power. So what happens with this? Suppose there is a remote village who are having very less people, and we need to transmit power from the normal grid to that location. What happens is if the distance is very long, most of the power that will be lost in the transmission itself, which we call it transmission losses. To reduce that, if we have the localized energy production on the remote area, then we are able to have, then the burden on the grid has been reduced. Even if we are also integrating power, so the local power also is generating and we are connecting it to the grid, so enhancing grid stability by providing supplementary power. So we are adding an extra power to the grid, so it is still stiff. Even then, the component of smart grid, smart sensors and actuators. So smart sensors, why smart sensors? Generally, we need to measure voltage, current, load. Load is by default, it is a power. In other words, if you completely split into that, like phasor measurement, power factor, a lot of other aspects will also come into picture. So what are the sensors that we use to monitor these parameters like voltage, current, and load? These sensors will actually give us more insight, and they actually improve the grid's operational efficiency and reliability. So you will get to know how much power it is actually consumed. So operational efficiency and even reliability also we can assist it. We can able to identify by enabling automated responses to detected issues. And finally, the communication networks. You can incorporate any technology like crucial for the real-time data exchange between various grid components. In a grid, a lot of other aspects, in a grid, a lot of things are connected like solar PV systems, power plants, users, electric vehicles, a lot of other things are there. For all these things, you need a real-time data exchange for which we need a communication network. So normally fiber optics or wireless communication is some technologies that we adopt for the communication. Ensure the seamless integration and coordination of all smart grid elements. As I said, so why if you incorporate these components, what are the benefits that we have? What is its importance as well? So enhanced efficiency and reliability, which we already have discussed. There exists a balance between electrical supply and demand. The smart grid optimizes this and the reducing waste. When we have a smart grid, the electricity supply and demand is, there is a proper balance is going to happen there. But still, when we are incorporating the renewable energy sources, there will be still a difficulty that we are going to see later. But on an outline, as soon as you are incorporating more power into the grid, then a proper balance happens there. In India, the demand is very high compared to the generation. There is still a lot of areas, like approximately 20% of the rural areas are still do not have the power, but they are still given the power supply connections. Still, there is still more. So when we are injecting the power or for the smart grid, the balance between electrical supply and demand can happen if there is a communication and all other aspects. In other words, the smart grid, if you have a smart grid, and there exists something called predictive maintenance. When we have a lot of data, like the power generation from individual aspects, how the communication, with the help of data and communication, we're able to do a predictive maintenance. So this communication can be done with by any methods like artificial intelligence or any technology. Using this maintenance helps in identifying potential failures before they occur. At the same time, it minimizes power outages and improves recovery times. So this is what a smart grid will give a feasibility for us in terms of efficiency and reliability. Now, when it comes to integrating renewable energy sources, this is what a lot of people are still involved to tackle this. So integration of intermittent renewable energy sources. Why it is being called intermittent? You cannot predict this. If it is solar PV, you cannot predict that you're going to give this much power at this time, but you can still forecast to some extent based on the previous data. So if the smart grid is trained with that, intermittent behavior, then we can still able to increase the reliability and efficiency. And even if we having the smart grid with integrating renewable energy sources, that you are injecting the power, more power, so dynamically to fluctuations in energy production from sources like solar and wind. If your grid is smart enough, then whatever the intermittent power that is being generated by renewable energy, you can still regulate it. So wind is generating random power right now, but if your grid is smart, it regulates that. How that is going to be regulated, we're going to see in the consecutive slides. Promote sustainability, sustainable energy use, and reduce carbon footprint. Obviously, when you have a sustainable sources like renewable, you are going to reduce the carbon footprint by reducing the dependence on fossil fuel consumptions. And one more thing, the importance of real-time monitoring and control. So it provides operators with insights. So there are different operators, transmission system operators, there are different operators at different places. So for them, if there is a real-time monitoring of the grid with instant insights into grid performance and health, so the smart grid will provide operators with these details, like how the grid is performing and what is its health. Health means whether it is stable, reliable, efficient, all these things. Allows for intermediate corrective actions in case of power quality issues. When you say power quality, one load have a high distortion rate that is going to affect another load. Suppose if we turn on, let us consider a small house. If a mixer grinder is turned on, sometimes you see a flickering in the tube light or some noise in the fan. So this is where a power quality comes. When the grid is very big, you have to consider the power quality. So when your grid is smart enough, it allows for intermediate corrective actions in case of power quality issues. If there is any power quality issues, how to do the corrective actions. These things will be given by these provisions we can avail with the help of smart grid. Again, it enhances when you use real-time monitoring and control. It enhances overall grid security through continuous surveillance. You're actually surveying it, you're actually monitoring it continuously. You can ensure the grid security. The last one, and very significant, consumer empowerment and engagement. When I involve smart meters, when the smart meters are provided to consumers, suppose in our all households or in some industries, if the conventional meters are replaced with smart meters, so we are going to have a detailed information on their energy production. So it enables consumers to make informed decisions about energy storage, and it encourages energy saving behaviors and increases participation in demand response programs. If you are able to cope up with my accent, please, it is fine. If it is not, please let me know in the chat box. If I'm speed, I'll reduce my pace. Okay. What are the core technologies in the next generation smart grids? As I said, whatever the conventional meters we have, we need to replace them with the smart meters that enables the data collection. A real-time data collection of electricity usage. Normally, how the power system works, they have some data that, and suppose now during the morning, they'll consider that in each house or in each industry, this much power consumption will be there. So there will be a command from the system operator to the respective power plants that you need to generate this much amount of power, so that power balance happens there. So it is like a predictive. But when the smart meters is there and you're able to collect the instantaneous data, most of the things will happen on the system itself, and it is very easy for the system operator to ensure the grid stability and reliability of the power, so that we will not have a power cut. Even the power generation, they are able to do it properly, efficiently. So this happens when real-time data connection of electricity, real-time data collection happens. That means there exists a two-way. So whatever the power I'm generating, whatever power I'm consuming, both the things need to be considered. Remote monitoring and diagnostics and enhanced billing accuracy. So whatever the billing that we have, it will be enhanced when we have a two-way communication system. Even the fraud detection can also be done. So there are some houses that I still see they bypass the meters. If you're if you're incorporating the smart meters, you cannot bypass such system, because billing accuracy will be improved and they can clearly identify the power consumption from each transmission line. Again, energy usage analytics. Here comes into the picture for the data analytics people. When I am having thousands and lakhs of houses, hundreds of industries, and everywhere I'm having the smart meters, if it is being enabled, consider the data that we are receiving for seconds, for minutes, for hours. So if you ensure the data, it is quite larger and you still have to manage all these details. So the data analysis for energy consumption patterns plays a key role here. And this also ensures the demand response and load forecasting. So we can say now currently this amount of power is happening. Someone has turned on washing machine in their house. So the nearby local distribution person can understand. So he have to give less power or more power in the upcoming time to ensure the stability. So personalized energy saving recommendations. So even they can say, now I'm using washing machine in the early morning, which is a peak time. So there can be a suggestion that we can shift using washing machine in the afternoon slot, so that the burden on the local distribution is reduced, so that even we will not be penalized on that case. So such things will be recommended when we have a real-time data monitoring, and if you're able to analyze the energy. Anomaly detection and proactive measures. So you have to do the proactive measures for all this. Again, the consumer interaction and feedback. When we have the metering infrastructure, advanced metering infrastructure, consumer interaction feedback will come into picture. I mean, it is a key role. User-friendly interfaces for energy monitoring, real-time alerts and notifications. So you'll get this, as I said, you are using a washing machine right now. So it is recommended to use it after 12 o'clock or after 1 o'clock. So they will give this time of real-time alerts and notifications. Or they will say you're actually over consuming the power, so you will be penalized with over surcharge. These things will be enabled to ensure proper saving or efficient and conversations and all this. So customer engagement through mobile apps, so they will be given everything on the mobile itself. So feedback mechanisms for utility performance. So if you say that some flickering happens, some low voltage happens, so such things you can give a feedback to the local distribution. So that feedbacks will actually help the utility to enhance their performance. The distributed energy resources. This is one of the dominant factor. Solar and wind energy integration. The solar and wind, they are actually intermittent sources, like their power cannot be estimated at a specific time. So how the people do is, they will give, suppose if I have a solar power plant, let us say in the house itself, let's talk about the individual house. In a house, I have 1 kilowatt of power connectivity, and currently I'm able to generate 500. But with the help of smart grid, the operator will say, or nearby distribution system, they will recommend, though I'm generating 500 watt of power, they will say 500 is too high, you can go for 400. Actually, this is not happening in small scale. When you have a solar power plant, which is in the range of megawatts, though my solar PV system with the help of MPPT methods, I'm able to generate a larger power. There is a restriction by the operator to generate the power. Consider, okay. So assume that you have the solar PV system is generating 50 megawatt, but the operator will restrict it to 40 megawatt only. That is because to ensure the grid stability. So if you are injecting more power, the voltage may rise. So he will ask you to generate 40. So this happens if the grid is not smart. When the grid is smart, even you will see to generate more power from the power plant. If you're able to give completely 50 watt, then I mean 50 megawatt, then you're actually getting more money, right? So why to compromise? So when the grid is smart, even this 40 can be converted to 50 by looking to the respective consumers. An example that recently Indian Energy Exchange has taken up, IEX. So assume that I have a solar power plant in Andhra Pradesh, and you want a customer, you have a customer at Delhi who want some power consumption at a specific rate. So though the Andhra Pradesh and Delhi are completely at two different parts. So there is a hospital at Delhi and your power generation is there in Andhra Pradesh because of government benefits or something. They have installed the plant in Andhra Pradesh and the hospital is there in Delhi. This power plant generation person can communicate directly with the hospital person that I'm going to give this much amount of power. So though the network is very complex, the energy exchange will help to uh, take the power balance there. I mean, it just acts as a mediator between the consumer and the generator. So assume that this is PV and this is a hospital. So the PV to hospital, the power is transmitted through the transmission grid. I mean, he is going to inject if the hospital requires 5 kilowatt of power. No, 5, let us consider 5 megawatt for the time being because consider it is a big hospital. And this solar panel is able to generate 5 megawatt. What does he do is, he will simply generate this 5 megawatt in Andhra Pradesh and corresponding 5 megawatt of power is being consumed by the hospital. But IEX is going to act as a mediator to transmit for the transactions, like whatever the power consumption transactions, that it is going to act as a mediator. So that is what, if this person is not communicating with the hospital, he is directly communicating with the transmission system. I mean, the like power grid. If he is directly communicating with the power system, they will say that you cannot inject more than 40 megawatt. But if you communicate with this hospital, you can inject till 50 megawatt also. Consider that there is a balance. So even this person has to have that maximum power. It is like they may have 5 megawatt. This is the plant should be at maximum value of 5 megawatt so that it is operated at fully loaded and the generator, I mean, the corresponding person is getting full value there. Okay, let's come back to the topic. I just want to give an example that we have recently experienced. So the solar and wind energy generation, they are highly intermittent by default, and grid stabilization is really a big challenge there. But still we can do when the grid is smart. So inverters and smart converters for efficiency. So we need, as it is a grid, which is AC system, and we can use inverters for it. And smart converters, when the solar is DC, so they generally use DC-DC converters, or a lot of DC-DC converters like micro, nano, and even sometimes small. It is like every panel will have its own MPPT converter to inject the power. So that inverters and smart converters for enhanced efficiency. Again, the net metering and energy credits. So whatever the power that is being generated, you have to see the meter over there, and whatever the energy that I'm giving, these are the credits. And grid parity and renewable incentives. So you'll get that incentives. When coming to energy storage system, so battery technologies is again another entity. We'll see that. So battery technologies and advancements, there is still a lot of research that needs to go for the battery technology, like what materials are going to have a higher energy density, a lot of other aspects that we can see in the upcoming slide. And peak shaving and load leveling. Generally, the battery power is going to be controlled. If you can control the battery power, you can regulate the grid power over the local region. So this intermittent, whatever the solar and wind generation, with the help of energy storage systems, so it actually aids this integration with renewable sources. An example that we use in the current industry, so we generally drive the vehicle, or we generally drive the electric vehicle with with the battery. But to enhance the energy production, I mean to have a higher energy density, we're going to incorporate solar panel system. So the load consider the load consumes 1 kilowatt, and panel is going to give only 200 watt. It's an example, it's just a rough value. So let us say I have my load like motors or turbines, whatever it is. My system is of 1 kilowatt, but I'm still my solar panel is able to generate 200 megawatt. So the other power, like 800 watts, which is the remaining power, is being given by the battery energy storage systems. It can be battery, it can be fuel cell also. So both of the things, with the help of them, we can inject power to meet the actual load. So these energy storage systems will help renewable energy sources like the solar or wind. It will support to integrate the renewable sources into the system. So energy storage systems is always a key aspect here. Okay. Okay. And microgrids and nanogrids. There are many cases that in Bangalore, a lot of local entrepreneurs who are taking the contracts from the government to install a remote electrification system. Like they will take the solar and wind systems and they will electrify a very rural region, like some tribal areas, some remote areas, where it is not, for the smart grid, it is not viable to transmit all the power. And it will take more time to transmit, to lay, to connect the transmission connect. Okay, I'll tell this way. So you have the rural area and the transmission grid is very far. Consider the gap is around 100 kilometers. This this rural area can have very less power, like 1 kilowatt. Assume that they only need lights. So even for this 1 kilowatt, transmit from here to here, it may take, I mean, the government will take time to release funds So that will be more time consuming. So before that, they will give some contracts to the or they will release some tenders so that some local entrepreneurs will come and electrify this village for this 1 kilowatt. They will use these solar panels and wind systems. So this village will be electrified with the basic necessities like the tube lights and fans. Slowly, the government is going to increase its transmission lines and it will connect the localized system. So it will have an extra power, localized power, but still it is lossy network. If we don't have the localized energy, it is completely lossy to transmit this 100 kilometers to deliver the 1 kilowatt power. But when the localized power is there, if the load demand is less, it can still reduce the transmission losses. So the microgrids and nanogrids are still a key aspect. Like nanogrids, you can say it is like 1 to 10 kilowatt. And sorry, nanogrids is of 1 to 10 kilowatt. And microgrids is more than like till 50 kilowatt, you can consider that. So localized energy generation and distribution, enhanced grid resilience and reliability. It enhances the grid resilience. Even when you have two power sources, if one is cut off, then you can have the localized power generation. And community-based energy solutions will happen. Again, integration with large grid networks. See, these small grid networks like microgrids or nanogrids, you can integrate with the actual power grid. So the next one, the smart sensors and IoT devices. Consider real-time grid monitoring as the previous version. So it does the continuous surveillance of grid parameters. At the same time, voltage and frequency monitoring, these two are very key aspects for the proper synchronization. And automated incident reporting, data-driven decision making is also possible. And again, the second one, when you consider the smart sensors and IoT devices, what other benefit do we have? What are the other application? Like you can go for the fault detection and isolation, rapid identification of the faults when you have IoT devices and smart sensors, and automated isolation and rerouting. So you can isolate and you can reroute back, and reduced outage durations. So you can easily detect that fault and you can isolate that specific aspect. So when you are reducing the outage, obviously you are increasing the reliability. So predictive maintenance. So you have to forecast the things here. So condition-based maintenance schedules. So based on specific conditions like the power requirement and the load demands. So there is a specific restriction on this power. So based on that condition, there is a maintenance schedule. So you have to maintenance this specific area. So that is possible when you have smart sensors and IoT devices, and downtime reduction through advanced analytics. Obviously, when you're doing the advanced analytics, the time will reduce. Asset life extension, obviously, when there is a reliable power and you're able to detect faults, you can actually increase the life. You can actually increase the life of that. And cost savings on repairs and replacements. So when you can properly identify a fault at a specific location, you can actually reduce the cost, right? So if you don't know where is the fault, so the cost will include to check all the places. And data security and privacy, this is very key aspects, and the engineers we are finding is very less. And it is a very key area in industry like data security and privacy. So encryption and secure data transmission is actually required. And regulatory compliance and standards. So there are different regulatory compliances and there are different standards that we'll see in the upcoming slides. So there has to be proper regulations. Now, instead of a regulated environment, we are moving towards deregulated environment. For example, every subsystem is going to behave autonomously. At the same time, the grid can have their autonomous incorporation into the grid. It is like grid is controlling the individual distribution, and individual distribution themselves are autonomous. For such things, there has to be some regulation. So regulatory compliance and standards is also required. So user authentication and authorization, this is one of the thing that still needs to be figured out. Because the regulations, what we see, there are some issues with this. So still user authentication and authorization, these things are involved in electric vehicle charging stations. Like if your vehicle is connected, yes, this person's vehicle is connected, and you have to see what is his power consumption at every time. So at what rate he is charging. I mean, is he charging frequently, like one day or for 2 days? So to identify that, a vehicle is given some identification. So even if there are different charges, suppose Benz is having its own charging station, and the Tata electric vehicles cannot connect to that charger. So it might create some problems. So there is some user authentication given to the vehicle, which will aid for the companies to be autonomous on their systems. And privacy preserving data analysis techniques. The very important one, and the forecasting one. This is a very less area in industry. This is a very key area that industry is suffering for. And still now the India research is going on this communication technologies for smart grid applications. For example, if you consider communication technologies, it is mainly of 4 types. What are the different communication technologies that we have, like wireless communication, or you're going for the Internet of Things, and how the data management is being done for that. What are the cyber security measures when such large data is available? How the cyber security is measuring has been taken. These are the 4 key areas and communications that you need to still see further. So there is something called LoRa, which aviation industry generally follows up. Sometimes we use 5G networks and LoRa. That comes in the range of sometimes 5 kilometers, sometimes 10 kilometers range. For this, how the communication is being happened. So this is one of the aspects, like wireless communication protocols. There are different protocols, out of which each industry follows its own communication method. So to enable smart grids, you can choose any of this, like LoRa, 5G, MBus, Zigbee protocol, or Wave, NFC, whatever the things you want. Bluetooth. Bluetooth is for very low range. So all these communication protocols, particularly wireless protocols, it helps in scalability and interoperability with existing systems. The next one, IoT. Every house is having internet. So you can have internet, you can establish your own Internet of Things into the system, like the smart grid integration. Whatever the meters that we have, if it is provided with the internet, so it comes under Internet of Things. So it helps seamless connectivity of grid components, and edge and cloud computing will come into picture. Whatever the data that we have to send it to the cloud, and there you have to process the data. And IoT enabled automated operations. So you can say that with the help of IoT, you can control any appliances, or even like the way you are controlling your home appliances, the smart grid can control the grid systems or subsystems. If you see here, the IoT in smart grid, let us see on a broad perspective instead of a small house. So you have energy storage systems, wind, solar, and power plant, all these things, if they are integrated with the Internet of Things, and there exists some virtual power plants that we'll talk later. So when all these things are being communicated, normally what happens, the power generated through the transmission line, it will be distributed to the buildings and industry. When it is IoT enabled, what happens what happens to it? It is seamless connectivity. You can simply connect them of grid components And by sending with the help of edge and cloud computing architectures, you can increase the smartness of the grid for reliability and efficient transmissions. So when you have, again, this much large systems, you need a communication systems that does data management and its analysis. So big data platforms, obviously, when we have almost hundreds and thousands and lakhs of consumers and producers, so you need to do the data management for this. So big data platforms and tools are required. Real time stream analytics, data warehousing and integration, visualization and reporting, all these things are very important in data management. When you have all this, obviously it is important for us to have a cyber security measures. So any threat detection and response mechanisms is one of the area that we are looking for. So security architecture and design principles, how you are going to ensure a secured transmission or secured communication. So you need to have an architecture for it, and how you are going to design, what are its principles. So incident management and recovery collaboration with cybersecurity organizations. So it is like the same thing. Uh, all the users, like industrial users, nuclear power plants, generators, and producers and consumers, all will be communicating with the some cybersecurity organizations to ensure secure transmission and high reliable power generation, high reliable power transmission. So far, we have seen the different technologies. Now, what are the challenges? So, it is mainly on the infrastructure modernization. So, let us say legacy systems compatibility issues. What is the legacy systems that we see here is now being, let us consider I am from Karnataka. The Karnataka has invested a lot of things in metering houses and industries. So there is a tradition that went till now. So it is the legacy that has gone. Now, if you want a sudden change to this, so you want to replace all the existing meters with the new meters. So the system should be able, I mean, the government should able to adopt, or the private organizations should able to adopt that, because that involves a very high cost infrastructure upgrades. That is not that easy to upgrade. Now we are in 5G technology and you immediately want 6G because it is developed. But it is not that easy to directly bring into the 6G technology in the real time. We have to see the possibilities. So there exists some time for it. So there is always a legacy compatibility issues, and again disruption during transition process. These are the key aspects in infrastructure modernization. Apart from this, as I said, there are some standards and regulations for the power transmission, for the smart grid enabling. So that is called interoperability issues. So there are different standards, you can say. So lack of standard protocols. There is no specific standard that you can follow this. So if you say IEC 61850, which is a substation automation standard, if you see it, so the main challenges that we see is limited scalability. We cannot scale to a larger extent. Okay. Next, distribution network protocol 3. So again, in this distribution, there are again some challenges, like it is not the cyber security issues are key in this distribution network protocol. If you can propose such things, it is quite easy. And the latest one, IEC 2030.5 standard. This is very latest one. It has a uh, better feasibilities. But the thing is, to incorporate this IEC standard, it is very complex into the current system. So such things are there. And if you consider MQTT, like message queuing telemetry transport, so this is mainly for the IoT standard that we are incorporating. Again, to incorporate IoT into the current system, it is again a tedious process. So there are some standard, we don't have, like each standard has its own advantage, but still, if you see the overall perspective, they still have the challenges. So integration difficulties with existing systems, all these standards, like you can say for subsystem automation, this standard, we cannot advance it that easily. So DNP, it has its own standard, but to integrate, everything has its own challenges. So integration difficulties are all there, all the way it is what, well, it is there. So vendor specific solutions hindering universal compatibility. Obviously, so there has to be some vendor who is giving some solutions to this, like a third party will come up and it will give a temporary solution for the company to enable this, to have a better interoperability. Again, data management and processing, handling large volumes of data efficiently. So you need a data management for that, and ensure data accuracy and consistency also. Whatever the data that we have, it should be accurate and it should be consistent to make a grid smarter. Implementing effective data security measures. So whatever the data that we have to ensure of better security of it. So the other challenge is economic and financial barriers. So when you're going for smart grid transformations, it requires significant capital expenditures. You have to replace the complete thing with a advanced system and limited access to funding or financing options. So it is very difficult to get the funding as well, and uncertainty about technology lifespans. You don't know how this much, if I'm incorporating a 5G technology, we don't know how far this 5G technology can support. Maybe if the 6G comes, if it is not that much worthy for me, I'll not go for it. So there is still some uncertainty over there. The next one is return on investment concerns. So lengthy payback periods. So there is a very long time to pay back our the investment. Difficulty in quantifying benefits. So you want some benefits and you have to know how much benefits you'll get it. So there is still difficulty and risk of not meeting projected returns. So there is one case study that I'm going to show on this risk of not meeting projected returns. On this return on investment, some person will give a solution for this. So one solution that I'll show in the case study. It's going very fast. Okay, financial incentives and policy support. It is okay, like I'm able to do all these smart sensors, advanced metering, renewable integration. But again, the government subsidies or grants are still insufficient, though they are giving a lot of benefits to the system. It is like in the initial cost, if you want to automate your house with the solar panels, or if you have good winds in your locality, if you want some wind turbines, so it is not whatever the government subsidies that you have, it is really not sufficient to have to reduce the burden on the producers, on small scale producers. It is still insufficient, and complex and restrictive loan processes. Still, they'll say that if you are incorporating renewable energy sources like solar PV systems, they will say you can go ahead with the government will always support for it, but still the process is really complex. You have to undergo a lot of things. Unless there exists a third party that leverage our work, it is not that simple to undergo that process. That means you have to claim for 50% subsidy from the government. If the government is giving 50% subsidy, that will not happen immediately. That will take some time. So even for that, you need to submit a lot of documents. So not just the documents, the time taking process, everything is being complex here. It is not that much liberal. And still, we still need some policy support on this case. So lack of tax incentives, still earlier for 1 year, if you are going for electric vehicle, the government has given subsidy of some value. If you procure an electric vehicle, you will get some incentives on it, like some subsidy if you buy some electric vehicle. But now the subsidy has been removed. Still, there is no tax incentives in this case. If I'm buying this and if I'm producing power, there is no tax incentives if I'm adopting the technology. There is still a barrier for it. And regulator and policy challenges, as again, now it like standardization and compliance. So you can see a lot of standards that I already discussed, varying standards across regions. Now, in US, suppose consider a state or consider a region, California, who have adopted some smart grid technologies, considering it has adopted advanced metering infrastructure, but still, whatever the policies and standards they have, we cannot adopt it. So everywhere, compared to for every region, they have their own standards. There is no universal standard that you can follow this for a faster production. And even costly compliance processes, they are really very costly, and frequent changes in regulations. So taking that, you will say that you're going to get subsidy of 50% subsidy in solar PV, or this is how a vendor, or this is how a power plant person is going to think this way, or even you're going to think this way. So you think that I may get my payback period in 5 years, but again there is a regulation change that instead of this much subsidy, they are going to reduce this. So there is a frequent changes in regulations that creates chaos. And privacy and data security regulations. Strictly, we don't have a proper data protection laws. Even anywhere, this has to be a primary concern that needs to be concerned in terms of data security. So complexities in cross-border data transfers. Obviously, when everything is different, it is really difficult. So it is very complex for cross-border data transfers, and high penalties for non-compliance. They will give a compliance standard, and if a bit deviation was there, the penalties are literally high. So that thing was not involved for data security. We don't such things. So if there is a data breach and some data was taken back or some data was manipulated, that might lead to grid failure. To ensure that, there has to be high penalties if it is not there if it is not complying to the standard. So market structure, still there are a lot of market structures you need to go, like monopolistic market tendencies are still there. So it is like a regulated environment is still in the system. You need to deregulate the system. Inadequate competition, fostering innovation, and skewed incentives. We still have to go for incentives deterring market entry. So if you want to enter, if you give incentives, the market will enter into the system. Okay. Now, what are the innovations and emerging trends? Predictive analytics for grid management. So leveraging historical data, whatever the data that we have, you have to forecast the energy consumption patterns. So you can say, compared to last year, there exists an increase in power consumption at a specific region. So this you can identify if you have the historical data. And again, enhancing grid efficiency by predicting peak load times. So obviously, when you identify the peak load times, you can obviously increase grid efficiency by injecting more power or by regulating them. So when you know, suppose you don't need to, suppose the power demand is too high, and now you have to ask the power plant to generate more power. So that again increase the operational costs. So if there exists a proper communication, and if you are able to predict the proper grid value, I mean proper power value, then you can reduce the operational cost as well. obviously now the big trend like AI for demand response optimization, whatever the demand that is the demand response that we want for, we have to incorporate AI technologies for optimizing this. How? Automating demand side response to balance supply and demand. So everything should be automated, like there has to be less burden on the system operator most if it is proper, if it is completely automated. And utilizing AI, if you adopt AI technologies in this, you're going to have energy saving recommendations and consumers. Everything will actually if you automate, then it going to give you more incentives, or it is actually benefiting your system. Enhancing load flexibility to prevent grid overloads. Obviously, you're going to have load flexibility here. Next, machine learning for fault detection. This is also one of the trending here. You have to train your system for identifying the fault, like implementing predictive maintenance to prevent equipment failures. Any equipment that is being done, if it is not working well, with the help of machine learning, you can implement the maintenance for it. Utilizing machine learning models to detect anomalies in real time, reducing downtime by quickly identifying and addressing faults. Obviously, you can identify it and you can address that. This is for next one is blockchain technology. Why do we need to adopt blockchain technology? So when you see a decentralized energy markets, what do you mean by decentralized? Like, as I said, individual local generations, consider our local distributor, power distributor, it is working autonomously, and grid is working differently. Grid is working on its own. So this is like decentralized, like we have given, the power grid has given some controls to the local group to decentralize them, so they can take their own decisions for the power generation or for power consumption. So such things, when the system is decentralized, like when there are more owners in the system, you need some technology to ensure a proper communication for enhancing the grid stability. So facilitating direct energy sales between consumers and producers. This blockchain technology will actually support in one of the aspect, like as I said, the solar power generation happens in Andhra Pradesh and the power consumption is happening in Delhi. So you can direct energy sales can be possible with the help of blockchain technology. Normally, blockchain technologies is used in cryptocurrencies. Now they are incorporating in the grid systems as well. And as I said, if I'm giving this uh, with this facility, you can actually reduce transaction cost by eliminating intermediaries. So let us consider Southern Load Dispatch Center, Regional Center, and SLRDC and NLRDC. Between these two, you can eliminate it and you can directly involve some third party to directly generate the power. When you are eliminating mediators in between, you can actually reduce the transaction costs. And this enhance transaction transparency and trust. Obviously, when there is no mediator, so you can say, obviously, there will be some leverage on that, and the cost to the consumers may increase. But if you get to know that there is a power generation of this much cost, like let us say 1 rupee per kilowatt hour, and you will get to know that, so you will say you're going to go for 1.5 rupee per kilowatt with the transmission cost includes. But if there are more intermediaries, so if there are more transmission system operators, then the cost will increase, obviously. And by incorporating this blockchain technology, you can enhance the grid security. So providing immutable records of energy transactions to prevent fraud. This is possible with the help of blockchain technology. and it improve traceability of energy sources for regulatory compliance. With the help of regulatory compliance can also be done properly. So strengthening cybersecurity measures through distributed leader technology. As I said, individual distributors themselves or the autonomous networks. So you can strengthen the cybersecurity when you have the transparency over there. Peer-to-peer energy trading. This is taking this. I'm going to show one case study of this peer-to-peer energy trading. So enabling consumers to trade excess energy with their neighbors. So whatever the energy that you have, you can simply transmit the power to the neighbors. But it is not that easy. There has to be some set of rules for this or some procedure to do peer-to-peer energy trading and encouraging the adoption of renewable energy sources at a local level. So it's simplifying the process of energy credit and deficit adjustments. We'll see this peer-to-peer energy trading now in one of the case study. So these are all like, if you see blockchain technology, you can decentralize the energy transactions. You can enhance the grid security and transparency. It also enables peer-to-peer energy trading. Like if you see, you're going to sell a Bitcoin and another people is going to buy a Bitcoin. So you two are independent entrepreneurs. There is no, I mean, the main person may not be there. So it is like peer-to-peer, person to person, you can consider that. This is possible with the help of blockchain technology. And what is this blockchain technology? It has two things like block header, block body, and again another block header, block body with the help of hash. Hash is something like you can see a bubble sorting algorithms using for loops or something, but hash technology is like in just one iteration, you'll get the solution. You will identify the required, or you will sort the things, you will identify the required element. So this is called hash one. If you are a programmer, you will get to know this. So in this block header and block header, there are two block headers, two block systems, and you're going to chain them with the help of this format of technologies, with this format of algorithms or structures, architecture can say. So if I adopt this blockchain technology, you can see its characteristics, you can programmable, whatever the things you want that you can evaluate. So you can say that this amount of price you can give. So that even that level of programming can be adopted in the blockchain technology. You can decentralize it. Like the local distributor can actually completely work with its consumers and immutable. So the validated transactions cannot be reversed. Once it is done, it is done. So you can say that I have consumed only this much power. No. So it is the transactions cannot be reversed, and this actually reduces the ambiguity. And timestamped, the transactions are timestamped. The consensus, the nodes have to give consent to validate a transaction. So there might be a mediator who have to give a consent to do a transaction, but still such provision is possible when you incorporate blockchain technology in this, and it is anonymous. So the identity of nodes is really not known from where you are getting this power. Those things is actually not necessary, and it is very secure. And recently, though the blockchain technology is very secure, there is a data breach in terms of cryptocurrencies that you can see that Wazirex has filed everything, like a lot of money theft has happened, but still the blockchain technology is very robust. It is still a secured system. So again, the communication technologies, so real-time decision making, reducing latency in grid operations, and enhancing data localization security. These are all what I call the amenities of the communication technologies. And advanced energy storage solutions. I'll go a bit faster. Time is less. So next generation battery technologies. I'm going to show what is the current technology and what things will come up with the next generation battery technologies, and integration of renewables is again an advanced energy storage solutions. So grid stabilization, when I can have my own power, everyone can have their own autonomous power. It is really hard for the grid to stabilize this, but still you can provide a better energy storage. When suppose you have an extra power, you can still have a better reliability over this. So resilience can be improved. So as I said, there are different types of batteries we have, like lithium ion, lithium polymer or lithium phosphate, lead acid. So these batteries, lithium ion batteries, they're actually used because of their high energy density. Because of their high energy density, they are actually being used in aviation applications or some where the weight plays a very key role. They are adopting lithium ion. Now solid state batteries are coming up. Compared to lithium ion, the solid state batteries have a bit advantage because in lithium ion there is a liquid inside it. If you are using a cylindrical lithium ion batteries, they are very dangerous, like they will blast very frequently. But if you consider solid state, the chance of this risk can be reduced if you incorporate lithium ion with the solid state. But still, solid state is not a completely evolved technology. It is emerging technology. So nickel cadmium, these are all like different. They have a different characteristics, but because of lithium ion higher energy density and its life cycle characteristics, they are adopting this. An alternative for lithium ion, you can go for lithium polymer. Lead acid, because of their weight constraints, they are actually being used for the household. So most of the households, they adopt lead acid.
Hello.
Yeah.
Yeah. So Ravani sir, a small thing. Actually, at 7:30 there is small another session will be going to start. So
Okay.
can you
Yeah.
quickly summarize that one, sir?
Yeah. Sure.
Thank you, sir.
So that is the next generation battery technologies. If you see the case studies and their implementation strategies, one of the way is, instead of the radial system, you can go for a ring main system to enhance the reliability. This is one of the system. But see, it is like battery energy management systems they have adopted to increase the reliability. So it is like if you see here, it is a radial system and it is a ringman system. Again, everything was decentralized. They have their own setup and you need a marketplace for it. So all these things will come into picture. Replacing this with this increase the complexity because you don't know a specific node for it. So it increases the complexity, but still it increases the reliability of the system. So as I said, there is one peer-to-peer operator where I can say, so I'm the consumer, I'm the prosumer. Like I can produce and I can consume as well. So for all these renewable, I'm having solar panels, someone else have wind. So I will forecast these details and I will create a grid pies for it. Now again, electric vehicles are also coming into the system. So what is the initial state of charge? So I have said, I'll consider that my battery is fully charged. I'm going to give this much rate for this. So accordingly, taking this, there will be a bid or offer given by these people, and based on the renewable energy generation, they are going to give an optimized risk. As I said earlier, there is something factor that you need to identify. This much risk will be there on the grid. So by considering these factors, you can actually integrate the power, or you can do the peer-to-peer energy trading. So that's something like post trading. That's a big concept. So you can refer this video at a later stage and you can understand this concept. And again, everything has their own regional standards, like North America has its own standards and Asian has its own standards, European has its own standards. So everything is a bit mess, like which standard to follow for better ensuring on faster development. So if you consider smart cities, there are currently evolved smart cities like Songdo, South Korea. Why? What things makes it smart? Like it is fully integrated smart grid system. Like it has smart meters, energy storage systems, and real-time monitoring systems. These are the things that it has adopted, and it is being calling its system as smart grid. And Abu Dhabi, it has involved renewable energy sources, energy storage systems, and they have a good demand side management systems. So Abu Dhabi has a different entity, but still they call themselves as smart city. So Denmark, like smart meters, electric vehicle charging stations, and energy storage systems, and they have incorporated this, and they are calling themselves as smart city. And if you see utility-led innovations, USA, California, and Ontario, Canada, they have adopted advanced metering infrastructure. Like every house, they have advanced metering system. But if you see PPP, public-private partnerships, India is now is in the what do you call it is in the prototype stage. Uh, that still needs to, I mean, it is accelerating the smart grid solutions, but still it is not yet evolved completely. And Ontario, Canada, they have deployed the smart grid technologies by adopting the advanced data management systems. So if you consider the major challenges and what adaptations do we need, low interoperability, cybersecurity, data management and analytics, integration of renewable energy sources, aging infrastructure. These are the key technical challenges we have. And economic viabilities, as I said, the funding, incentives, government incentives, all these things will come, like government incentives. These are all very key aspects for the smart grid. And what are the upcoming trends? A very simple format, I can say. Quantum computing is some alternative which is least explored by the industries, and if they are being evolved with the researchers, then we'll incorporate that things in the industry, but a product has to come out with that, or a service has to come out with that. Even now the system has to integrate the 5G networks, which is the latest network, so for a faster and more reliable communications. If you see, the next one is evaluation of automated systems. Every system should have its automated. That can be done with the help of AI and machine learning systems for predictive maintenance. So if you see the future regulate policy and market evaluation technologies, future regulatory frameworks, like there has to be proper guidelines. And if you consider economic incentives, tax incentives, and subsidies for renewable energy adoption, whatever we have, we still need a bit more for better encouragement of smart grid and international cooperation standards. There is no harmony. Like everyone has their own standards for them. Like European Union has their own standard, America has their own standard, India has their own standard. So there is no harmony in the universal standards. So there has to be some standards. By collaborating that, we can make the grid, we can evolve this market even better. So if you consider the long-term vision, sustainable and resilient infrastructure is required. So that helps us in disaster resistant infrastructure designs. We have to design better system for it, and eco-friendly and durable grid components. We need to develop such things. If you consider proactive consumer participation, incentivizing consumer engagement is again another entity, and holistic grid management solutions, integrated systems for seamless operation of generation, distribution, consumption. This integration should be seamless between the generation, distribution, and consumption. Thank you. I think I have sped it up. Thank you. If you have any queries, you can ask for the same.
Thank you so much, sir, for your valuable presentation. Is there any questions from participants, sir? You can interact to with Dr. Bhanuprakash, sir. If you have any queries, you raise your hand. Yes. Dilip sir, you just please continue your query, sir.
Sir, good evening, sir.
Very good evening.
Sir, machine learning can be used to identify new materials with desirable properties, sir, by screening large database of materials. The
What do you
ML
mean by
model,
materials here?
sir, in my case, thermal energy storage system, sir.
Okay.
For that case, I need some database which contains properties of materials and like energy density and other things. So that's also used for development of batteries also, sir.
Okay.
For this
Such
case,
tech.
I need a property database and large computation facility, sir. Where can I get these database access and computation facility for machine learning techniques, sir?
NIT Trichy is having this data center. I mean, they have this. Uh, I mean, a lot of institutions like IITs and NITs, they
Yes, sir.
have this computation technologies. You can approach those industries. I mean, industries also. Suppose to procure such large data centers, I mean, to compute such things,
Sir.
will generally go to the universities or some third-party vendors to do our processing and will come back. So you
Sir.
can go to top IITs for that.
A property database from various foreign universities, Cambridge University, like they have, sir.
You have to explore that. See, there are some, each faculties will have some own laboratory. You can see the equipment. Some will disclose that information. So accordingly, you can approach the professor and you can do the process.
Okay. Thank you.
Yeah.
Yeah, any other questions from audience side? You can text the message also in the chat box. I hope there is no queries. There is no query. So, Dr. Subramanian sir, you just continues.
Ravi?
Yes, sir.
Ravi?
Yes, sir.
Any queries from the other participants? No.
I hope there is no queries, sir. So,
Oh, please proceed.
okay. So, on behalf of all the participants, I would like to express our sincere gratitude to our esteemed resource person for delivering an enlightening session on smart grid systems. Your detailed discussion on the integration of advanced technologies, intelligent monitoring, and efficient energy management within the smart grid has provided us with a deeper understanding of this transformative field. The practical sessions you shared on the challenges and opportunities in implementing the smart grid solution, along with examples of real world application, were truly valuable. This session has broadened our knowledge and inspiring us to explore the potential of smart grid systems in modern energy infrastructure. Thank you once again for your sharing your time, expertise, and innovative ideas with us. We hope to learn from you in the future session as well. Thank you, sir.
Thank you, the coordinators and participants for being patient, and thanks for ATAL and thanks to your college for giving this opportunity to me. So with the better times, I'm going to give you more and more proper case studies that I have figured it out or that I have collected. I would like to share the things for the researchers to enhance their research.
Thank you.
So
Thank
thank
you,
you all.
Dr.
Yeah.
Prakash Garu. So on behalf of MEZR College of Engineering and participant, I would like to extend my heartfelt gratitude to you for an engaging and insightful session on this next generation smart grid technologies. The advancements in this domain, as discussed today, are not just shaping the future of energy management, but are also pivotal for achieving sustainability goals globally. Thank you once again, sir, for your valuable time and contribution to this session. Thank you so much.
Yeah, thanks a lot.
Sir, can you please hold for a few seconds? We'll take a snapshot with the expert. So can you switch on your video as well?
Yeah, 1 minute. Am I clear?
Yeah. I request organizing committee members, can you take the snapshot? Please hold for 5 seconds, sir. We are taking the snapshots. Yes, sir. My job is done. Thank you, sir. Thank you so much for your valuable insights. I hope in future we can have more sessions in this smart grid energy technologies. So thank you so much, sir. You can sign up this session.
Dr. Ravi.
Sir.
Please proceed to the next session. Sir is already joined.
Okay, sir.
Sir, welcome to Professor Anil Kumar. Sir, is it audible to you?
Yeah. Good evening, all. Yeah. Can you hear me?
Yeah. Okay. Dr. Ravi? Dr. Ravi Kumar.
Yes, sir. I'm in
Please
online.
proceed.
Yes, sir. So good evening to everyone present here. It is my privilege to on and introduce an eminent academician and distinguished researcher, Dr. E. Anil Kumar sir, who has made significant contribution to the field of mechanical engineering. Dr. Anil Kumar sir is currently serving as a professor in the Department of Mechanical Engineering and Dean of Sponsored Research and Consultancy at IIT Tirupati, a role that underscores his commitment to both academia and industry-driven innovation. Dr. Anil Kumar Sal holds his PhD from a prestigious IIT Madras, where he has laid the foundation for his remarkable academic career. He later held esteemed positions as assistant professor and associate professor at IIT Indore, where he also served as associate dean of academic affairs. His visionary leadership is exemplified by his pivotal role as a founding head of the mechanical engineering department at IIT Indore and IIT Tirupati institutions. With a deep passion for research, Dr. Anil Kumar's expertise spans critical areas such as thermodynamic and thermophysical properties of solid-state hydrogen storage material, thermal energy storage, carbon dioxide capture, and sorption heating and cooling system. As he has authored over 100 research papers published in reputed international journals and conference proceedings, making substantial contributions to the global knowledge pool. His excellence in research is further reflected in the successful execution of 8 sponsored research projects worth over 3 crores, with more promising projects in pipeline. Dr. Anil Kumar sir influences extended beyond research and teaching. He is an editorial board member of Wiley Journal Energy Storage and a review committee member for the Technology Mission Division of Department of Science and Technology, India. His service as a reviewer for over 200 journal articles from renowned publishers such as Elsewhere, Springer, Wiley, Taylor and Francis demonstrates his dedication to maintaining the highest standards in the scientific research. Dr. Anil Kumar sir illustrious career is a testament of his unwavering commitment to excellence in education, research, and innovation. His contribution continues to inspire students, researchers, and fellow academicians alike. Let us extend a heart welcome to Dr. E. Anil Kumar sir, whose expertise and insight will enrich our learning experience today. Thank you so much, sir, for introducing, for giving an opportunity. It's an honor to me to introduce your profile. So I hope this session will be definitely helpful for that so many research peoples and faculty members. So please continue your session, sir.
Yeah, can you see my presentation?
Yes, sir.
Yes, sir.
Yeah, thank you. Good evening, everyone. It's a long day. Of course, every day is a long day for you in this workshop. So I gave a small introduction about the necessity of energy storage technologies in my introductory remarks during the first day. So today I'm going to talk more comprehensively on the hydrogen storage technologies. You might have heard about the National Hydrogen Energy Mission. Our Honorable Prime Minister has announced it nearly a couple of years back. Okay, and the Indian government also realized the importance of bringing hydrogen as energy carrier or integrating the renewables or with the end users. So with that motive, government has started this National Hydrogen Energy Mission, and there are many. Subsequently, there are many calls both from DST, MNRE, mainly from these two ministries. So they have announced the National Hydrogen, hydrogen valleys. At least for one per the state, they have given hydrogen valleys. Now there is recently a call from MNRE and Center of Excellences on Hydrogen. Okay. So apart from that, DST is regularly giving hydrogen fuel cell call almost every year. So there are many research opportunities, funding opportunities, and not only for academia, even for the industry. Government is going to subsidize and they're going to support a lot of R&D activities in this field. So to realize hydrogen as a kind of a buffer energy storage or a energy carrier, there are many challenges. I'm going to address some few of them during this talk and share some of my thoughts and my research experience for the past 20 years. I started my hydrogen storage research about 2004 when I joined as a PhD graduate at IIT Madras. So whatever the exposure I have, the knowledge I gained for the last 20 years, I'm going to put it in a brief way through these presentations. So let me to start with the world energy requirements. We know that energy is required for everything, from day-to-day activities to industries, for manufacturing the products, for even now without electricity or energy, we cannot sit here and discuss it like this over online, right? So primarily all these energy requirements we are meeting using the fossil energy sources, whether it is generation of electrical energy or for transportation or cooking. You take any of our major energy requirements, mostly even today we are meeting from hydrocarbons. And we know that majorly these hydrocarbons are coal, petroleum, natural gas, etc. And we study in school days itself. It takes few millions of years to form these natural resources, either coal mines or petroleum, etc. But right from the start of the industrialization, about 200 years back, we started using them at a rapid rate. Now, the rate at which we are digging out these hydrocarbons from under the earth and we are burning is aggressively increasing, and it is leading to the emission of more anthropogenic CO and CO2 into the environment. So it is not only depleting the available energy resources, which has taken a few million years to form, but also possessing the air pollution problem or global warming problem, on the earth. So we have to move from these fuels to the renewable energies. Of course, there is a substantial differentiation between these two, not only renewable sustainable fuels, we say solar and wind, but the major thermodynamically, if you see the major difference between these two are the exergy content of these fuels. And generally, these natural resources which are depletable and fossil are high in exergy content per unit mass. They contain a lot of energy. They are not spread over. Exergy content is high, but whereas you take solar and wind, exergy content are less when compared to this per unit mass or per unit area basis. But nevertheless, they are sustainable. Okay, so as I told, they are highly intermittent in nature. It is very difficult to bridge the supply demand gap. Sometimes we may require more energy, whereas the supply will be less, or we require less energy, the supply may be more. So this gap we have to effectively fill. We require good, efficient, environmental friendly energy storage technologies. Okay, so there hydrogen is going to play a very good role. We'll see how it is. So if you see with respect to the transportation sector, this is one factor which is worried mostly in cities, because the air quality is decided by the transportation. One of the major factor, maybe 32 to 40% of the pollutants in cities at least coming from the transportation sector. So this sector is growing, every year. Especially if you take worldwide or China or India, this is a bit old journal article, graph taken from old journal article, but nevertheless the trend is same. So the rate at which these automobiles coming onto the road are increasing, whereas the need for the petroleum is substantially increasing, because mostly these are dependent on petrol or diesel, or to some extent the natural gas. Okay, so in cities, when this the population of the automobiles are increasing, that is possessing the more pollution problem also. Okay, in two ways, if we see the energy bill, is very high, because we are mostly importing these petroleum products. The second thing is the living standards, the air quality in the cities are in danger because of the use of these fossil fuels, especially for transportation applications. So if you see what are the different alternatives to mitigate the petroleum requirements, or petrol, diesel, or natural gas, petrol and diesel requirements. So these are some of the possible options, the increasing the efficiency of the conventional fuel systems. Okay, so this has been happening for the last 150 years, right from the invention of the Otto cycle, diesel cycle, or even gas turbine cycle. A lot of engineering efforts has been undergone to increase their efficiency, and we know that the maximum efficiency of any heat engine is given by the Carnot engine, which says that 1 minus heat sink temperature divided by heat source temperature. So there are efforts to come nearer to this by using a higher temperature where these mission engines are operated. But using higher temperatures are always associated with the thermal stress problems for the materials. The materials should be able to withstand higher temperatures for longer durations. Not only that, thermodynamically as well as heat and mass transfer wise, all these devices are optimized to come neither to the thermodynamically possible limit. But nevertheless, that gap is still huge, because if you take a combined power generation cycle, which is having a efficiency of around 40-45, whereas the Carnot efficiencies for the temperatures at which they are operated ranges from 60 to 70. So still there is scope to increase the efficiency of the conventional system, but we are almost reaching a kind of a a practical saturation point. Thermodynamical saturation point is something different, which is a higher benchmark, but we are almost reaching a practical saturation point because the increase in the efficiencies, whatever we do are very small, very minimal. Of course, now we are building the ultra high critical steam power plants where the maximum temperature in the cycle can go up to above 700 degrees centigrade. Thereby, we can increase the efficiency substantially. So the other option is CNG. Of course, this is already in place in many of the metro cities. The problem associated with CNG is, again, this is also a fossil fuel, but maybe less polluting when compared to petrol and diesel. Of course, distribution is a problem. We have pipelines. The compressed natural gas can be distributed through the pipelines. The third option being the biofuels. A lot of research has been going on biofuels also. So these are basically from some plant-based oils which can be mixed with the petrol or diesel, or even they can be used directly. So Indian government has also set a target of mixing at least 20% of the biofuels. Thereby we can reduce the oil imports by 20% by 2025. But there are still some engineering problems associated with the biofuels because they are high viscous. The atomization is not so smooth like petrol or diesel. So still a lot of research is going on using the fuel blends or, studying the combustion characteristics or atomization characteristics of the new fuels or mixture of fuels. Then comes the electrical vehicles. Now we are already seeing this transition from the petrol-based vehicles to the electrical vehicles, because even the government has realized that we can reduce the pollution by using the electrical vehicles. The major challenge with the way electrical vehicles is the battery is the major component, a bulky component and costly component. So a lot of research has been happening for the last 20 years to increase the energy storage capability of the. Just a minute. Yeah, the energy storage capability as well as the power density of the batteries, the rechargeable time, and the number of cycles it can be recharged has increased tremendously last 5 to 10 years. And so that we are slowly moving, especially for two-wheelers and four-wheelers, we are lighter vehicles. We are moving from petrol and diesel-based vehicles to electrical vehicles. Still, the range is a concern for many people because if you want to go for longer rides, there is always consciousness about the charge of the battery. Okay, hopefully there will be some developments because as of now, like lithium-ion batteries being used for electrical vehicles. There are other chemistries are also coming up like lithium sodium or some other chemistries which can store much more energy compared to the lithium ion batteries. So their cyclability and stability need to be still improved. So however, there is going to be a disruptive change in the vehicular market in all the countries towards the electrical vehicles. And if you see the mechanical engineering problems with respect to the electrical vehicles, of course, the major problem is in battery package, making the battery package more thermally efficient. So that, while discharging or charging the batteries at a higher power rate, the temperature won't go beyond the safety limit. They are well maintained within the safety limit. So with respect to the research opportunities with respect to batteries are, one is the chemistry, the battery chemistry, developing different anode, cathode, and electrolytes for batteries with longer life and ease of charging, number of cycles it can be charged, and the packing of these battery cells, battery management systems, developing proper battery management systems. So there are quite opportunities are there. Even recently, the ANRF has given a call for the for the researcher to develop clusters on electrical vehicles. So basically, they have given three verticals. One vertical is batteries, developing the new age batteries. The second one is power drives, and the third one is battery management systems and managing the charging stations. Okay, so there are quite a lot of R&D options are there in this field also. Then coming to the topic of the day, hydrogen as a carrier for transportation. So you might have already seen there are very good videos now, especially in Europe or China. They're operating the hydrogen-based trains also. Then we are seeing hydrogen vehicles, hydrogen fuel cell vehicles. So one advantage when you see compare the battery-based vehicles, that is battery and hydrogen fuel cell based vehicles is hydrogen fuel cell based vehicles will be having a longer range, because if you can store more amount of hydrogen, you will get the range is not a problem, so you can use it for longer drives also. The other thing is, if with respect to batteries, now we are moving towards batteries because again lithium is kind of a rare earth, limitedly available metal. Of course, it is again concentrated, and few countries only has a hold on that, like China. But of course, we can develop new new battery chemistries. But the major challenge is what we will do with these batteries once their life is over. Again, it poses a challenge for us. Like we are facing problems with the use of polythene, plastics, etc. So after down the line, maybe after 25 years, 30 years, we will realize that how we can handle with this the batteries whose life is over. Of course, we have to recycle them. Of course, 100% recycling is not possible, and recycling comes with a lot of costly and other byproducts during the recycling. Okay. So there, little bit advantage is present with respect to the hydrogen vehicles. Though the battery vehicle technology is much advanced compared to the hydrogen fuel cell based vehicles. Okay, so in this talk, we will see what are the challenges basically to make it more efficient, or how to bring them into the market, make it more commercialized or price competitive, when compared to the petrol or diesel based vehicles. If when it comes to hydrogen and fuel cell based vehicles. So why hydrogen? So any fuel we know that is a mixture of carbon and hydrogen majorly. As we move from fuels which are purely carbon, mostly carbon is coal, which is solid based, and when number of hydrogen atoms in the molecule increases, it becomes slightly lighter, so it becomes first oil. When hydrogen atoms further increases within the molecule, it becomes a gases, means further lighter, it becomes a natural gas. Okay, so when there is no carbon atom in the molecule, it is a pure hydrogen. So as we are moving from molecules of higher carbon to the molecules of lesser carbon, the calorific value or heating value of the fuel increases, and the pollution reduces. Okay, so these are the advantages. So if you see in that way, hydrogen is if you have a pure hydrogen, it is when we are using it for energy, harnessing the energy from hydrogen, it is we can say it is environmental friendly. But here again, the catch is the hydrogen should be obtained in an environmental friendly way without polluting the environment. So when we have pure hydrogen, it is eco-friendly. It is having higher energy per unit mass because, as I told, the calorific value increases when you oxidize carbon and hydrogen. The energy released when you oxidize hydrogen is much higher when compared to the carbon. So because of that, per unit mass, the hydrogen has higher energy density, And of course, hydrogen is abundant, not as a free element, and it is mixed with either oxygen in water or with carbon in all organic compounds. Okay, so if we compare the thermodynamic properties with the other fuels, the heating value, as I told, the amount of energy that releases when we burn 1 kg of fuel, it is almost thrice that of the petrol. Okay. So that's why it has higher energy density per unit mass, and it has a longer air fuel ratio. Ignition takes place over a longer air fuel ratio. The major challenge is also with the diffusion coefficients of the air, of the hydrogen in air. So since it is the lightest element, it can diffuse very fast, and it is odorless and colorless. So it is very difficult to realize that hydrogen is being leaking. So there are no reagents which can diffuse at the same rate as the hydrogen is doing. Okay. So hydrogen detection, leakage detection is a major challenge. Of course, there are nowadays we have good sensors. So if you have a sensor, if there is a hydrogen leak, it gives a warning that there is a leak or the hydrogen concentration in the air in that environment is increasing drastically. Okay. So as a fuel, it has good characteristics because it has higher energy density per unit mass. But what are the challenges to realize these hydrogen as a energy carrier for different applications? So one is producing hydrogen in a environmental friendly way, in a cost effective and efficient way. Okay. So we'll see briefly what are the different production methods. So what are the challenges associated with respect to the hydrogen production? What are the research opportunities available with respect to the hydrogen production? Of course, utilization. Utilization we can use by burning in IC engines or fuel cells. Of course, IC engines, a lot of work is being done at ARAI Pune, to use hydrogen directly into the engines with internal combustion engines. The second option is the fuel cells, which directly converts the chemical energy present in hydrogen into electrical energy. The fuel cells are more efficient when compared to the IC engines. But if you see the cost wise and durability wise, the fuel IC engines may become a winner, but at present fuel cells are the looking better option because of the higher efficiency of energy conversion. So we'll see very briefly about the hydrogen production. We'll concentrate mostly on hydrogen storage, especially for transportation applications or for stationary applications. These are the present technologies that are available for hydrogen production. This is a very brief note only about the hydrogen production. There are many methods are there for hydrogen production. But as on today, the most of the about 50%, half of the hydrogen produced is from steam reforming. Of course, it is a two-step reaction. We convert this natural gas into carbon dioxide and hydrogen. Then again, carbon monoxide is again has a water shift reaction. So it gives carbon dioxide as well as hydrogen. So most of the hydrogen, 50% of the hydrogen produced is by this method. The problem with this method is still we are using the fossil fuels and releasing carbon dioxide. And this is the cheapest way we can produce hydrogen. Okay, the cost of the hydrogen is much cheaper in using this method out of the available hydrogen production methods. Then partial oxidation of heavy hydrocarbons, it's a similar process, and partial oxidation of the coal. This is with respect to Indian context, this is a very good method because Indian coal has more ash content, sulfur content. So we are not able to use directly for burning because still we import coal because of those reasons. So, but if we can gasify this coal in situ within near the coal mines and convert this into useful fuel like hydrogen, gaseous fuel like hydrogen, then it becomes more cleaner. But during all these three processes, it is very important to capture the CO2 and sequestrate the CO2. Otherwise, we'll be releasing a lot of CO2 into the environment. And the hydrogen produced using the fossil fuels with the CO2 emissions is called as gray hydrogen. And if we capture the CO2 by some means and sequestrate it, won't release it into the environment, it is called blue hydrogen. Okay. So capturing and sequestration requires extra cost. It adds up to the extra cost. But nevertheless, it is important because our intention is to mitigate the CO2 emissions into the environment. So the cleanest method of producing hydrogen is cracking the water into hydrogen and oxygen molecules. Of course, this is it gives a pure hydrogen, almost 99.49 or 59 hydrogen. That means 99.999999% pure hydrogen. But it's a kind of a costlier process because the energy required for the electrolysis is high grade energy, electrical energy, and the energy required for producing kg of hydrogen is much higher. So because of that, it's a still costlier process. If you see cost wise, if you have a gray hydrogen which you are producing using without carbon capture, it is almost 4 to 5 times higher cost wise. So we should able to bring down the cost. To bring down the cost of the electrolysis, we need to develop energy efficient electrolyzer. So electrolyzer is a device which splits the water into hydrogen and oxygen molecules. So indigenously, we don't have technology to develop high capacity electrolyzers. Of course, people are buying from outside the high capacity of few gigawatt capacity electrolyzers they are installing. Reliance is installing a plant in Gujarat, and many corporates has come forward to produce green hydrogen from solar plants, especially. So from these present day technologies, we should be able to move towards the future technologies where we should be able to use biomass, of course, solar and wind using electrolysis process. Biomass also a lot of research is going on through gasification methods or biohydrogen production through algae. And of course, nuclear has its own advantages and disadvantages because you can produce electrical energy from nuclear energy. Again, it is kind of a quoted question mark, how safe it is environmentally, how to deal with the nuclear waste, all those things. So I see at least the opportunity is there with respect to having a larger solar plants or wind plants and producing green hydrogen from it. Maybe one of the future options to move towards cleaner fuels for transportation applications. Okay. So with respect to production, yes, there are many research opportunities. One is developing the electrolyzers, higher capacity electrolyzers, and then producing hydrogen in a cleaner way through biomass route and integrating these electrolyzers. If you take electrolyzers, integrating the electrolyzers with the solar and wind farms. Okay. So if you are able to produce green hydrogen, let us say in an environmentally friendly way, in a cost-effective way, the cost should be comparable with the present fuels like petrol or diesel. It should be. Otherwise, everything depends upon the cost. If it is too high, people won't ready to buy it immediately. It's very difficult to move towards that direction. So we should be able to move, make it more cost effective. So we should be able to reduce the cost of hydrogen production in a cleaner way. Okay. So once you have hydrogen, as I already told, it has a higher gravimetric energy density. Per unit mass, it has large amount of energy when compared to the other similar kind of fuels like petrol or diesel. But the challenge is, then what is the challenge? With respect to hydrogen utilization, the storage of hydrogen is a major challenge because per unit volume, it has a very low energy density. That means if you take at a normal temperature and pressure near atmospheric conditions, it has a density of 0.0189 kg per meter cube. You can assume a meter cube size container being engineers, we can see 1 meter cube in all the 3 directions. If you take that much bigger tank at normal room conditions, you can store only 18 grams of hydrogen. It's very, very small, at 1 atmospheric pressure and room temperature, we can store only 18 grams. Whereas if you see the petrol tanks, in a small tank, what we put petrol, about 10 to 15 liters petrol, and we can drive the vehicle. If it is a two-wheeler, we can drive roughly 500, 600 kilometers before it needs to be refilled. So in such a big tank, if we are storing hydrogen at atmospheric conditions, we can store only 18 grams of hydrogen. It's very small. It is not sufficient enough for any application. So we should be able to increase the volumetric energy density of hydrogen. That means in a given volume, we should be able to store more amount of hydrogen. And how we can do that? If we take a smaller volume, we want to carry a smaller tank, for transportation applications, either with a two-wheeler, three-wheeler, or four-wheeler. In that small tank, we should be able to store sufficient amount of hydrogen so that we are able to run the vehicle for a certain distance, right? So how we can increase the volumetric energy density? The one method of doing it is compressing the hydrogen, compress it to very high pressure, maybe 700 to 800 times the atmospheric pressure. So 30 to some 80 megapascal it's showing, pressure. That is about 800 times the atmospheric pressure. So if you are able to store at that pressure, yes, you can run a four-wheeler maybe with single charging. You may be able to run about 400 to 400 miles, about 600 to 700 kilometers. So the challenge associated with the compression of hydrogen is we have to compress to very high pressures. So we require a lot of energy. So from where this energy is coming from again? If you are using mechanical compressors, you need to use electrical energy again to derive that mechanical energy and compress the hydrogen from the electrolysis output to such a high pressure where we can store in the container or gas cylinders. It requires a lot of mechanical or electrical energy. Of course, if you see the energy content wise, it takes up almost 25%, 1/4 of the hydrogen energy, which we can obtain from it by through fuel cells. By using fuel cells, we are producing energy. We are converting that into mechanical energy, thereby electrical energy directly. So if you take to compress, it requires 1/4 of the hydrogen energy present in the cylinder. Okay, such a high amount of energy is required. But nevertheless, right now it is being done using the compressed cylinders only for all the cars which are coming or with coming with high pressure cylinders. So the other technical aspect is we should be able to develop these cylinders. The cylinder should be lighter. It should be able to the weight of the cylinder itself should not be too high. It should be lighter and it should be able to withstand hydrogen, which is highly permeable, highly diffusible, because it's a very, it is the lightest element. Even a very small gap, of few microns, the hydrogen can come out. So it should be leak proof. It should be light. It should be able to store very high pressure, withstand very high mechanical stresses. It's not so easy, but still people has developed these composite cylinders which can be where we can store hydrogen at 800 bar. The major challenge is, of course, we have the technology indigenously. Also, we can manufacture these composite cylinders. But the challenge is we're testing them. We don't have any testing facilities within India. Now at least the community is thinking about establishing the testing facility for for testing these cylinders. Once you manufacture, we should be able to prove that they withstand hydrogen pressure, because withstanding water pressure is different. Withstanding hydrogen pressure to up to that level, maybe we have to test it twice the pressure at least to have a safety limit up to 800 bar. Okay, the testing is a major challenge once we develop the cylinders. There are research groups working. One group is working at IIT Kanpur, one group is working at IIT Bombay in developing these type 4 cylinders. These are all called type 4 cylinders. General commercially available hydrogen cylinders, they are metal based. They store up to a 150 bar of hydrogen. But if you want to scale up to thrice the pressure, so we need to develop these high pressure cylinders indigenously. So that is one challenge with respect to the hydrogen compressed hydrogen storage. And we need to develop the technologies where we can compress the hydrogen easily, using less energy to such high pressures. So we are also working at IIT Tirupati, developing hydrogen compression technology using thermal energy. So I'll tell briefly about that research in the coming slides. So where we can use the heat energy of, or thermal energy, hot fluids even up to 100 degrees centigrade to compress hydrogen up to some 300-400 bar. So compression is one way of storing hydrogen, where we can increase the volumetric energy density by compressing the gas to high pressures. The other method is liquefying it. If we can liquefy the gas, its density further increases. Okay, of course, liquefaction means we have to, at atmospheric pressure, we have to take hydrogen down to 20 Kelvin, which is about minus 253 degrees centigrade. Okay, so such a low temperature, cryogenic temperatures, we require, of course, cryogenic facilities. Either we should able to use, cascading vapor compression refrigeration systems, or mixed refrigerant cryo coolers using Joule Thomson expansion. So these methods can be used. Of course, they are still, they are also highly energy intensive, because to liquefy the gas, we have to compress it to very high pressures. Then we have to expand it and liquefy the gas, liquefy hydrogen. So, and again, these liquefied hydrogen has to be stored at 20 Kelvin, which is much lower temperature. Suppose you have a liquid hydrogen tank at 20 Kelvin, whereas the outside temperature is room temperature, normal temperature, let us say 300 Kelvin. So about 280 Kelvin temperature difference is there, in between the inside hydrogen environment and the atmospheric, which is outside. So there will be always heat loss into the tank, and some hydrogen transforms into vapor. So when this hydrogen is transforming into vapor, that starts building up pressure in the hydrogen tank. So to keep the pressure to a safer level, we have to let some hydrogen go out. So that is called boil-off losses. So there are challenges still. One is it is highly energy intensive. It requires a lot of energy to liquefy the hydrogen, and while storing also there will be boil-off losses. But nevertheless, liquid hydrogen is used for space applications, okay, to run fuel cells, or liquid hydrogen itself is used as a fuel. Okay. So Airbus, which is the one of the aircraft manufacturer, along with the Boeing, has announced that their aircrafts will run by 2035 using hydrogen in the liquid state, by carrying hydrogen in the liquid state. Of course, they want to work on these technologies to come up with energy efficient liquid storage of hydrogen. And there are many startups which are working to develop hydrogen and fuel cell based vertical lift aircrafts also. So there also they are, but right now they are taking hydrogen in gaseous state only. Like drones, where we can take passengers as well as heavier goods by vertical lift, not horizontal lift. It's a vertical lift aircrafts like drones. Then the third option for storing hydrogen is solid state storage of hydrogen. So there are materials which adsorb as well as absorb hydrogen into them. So adsorption is a physical phenomena where just gas goes and sits over the surface of the molecule. Whereas absorption is a volumetric phenomena, because the gas goes and sits in the interstitial space. So the example for adsorption based materials are all carbon based materials like activated carbons, graphene, graphite, single wall carbon nanotubes, multi wall carbon nanotubes, because they are porous, they have larger surface area over the surface. They are able to force can extract hydrogen and it just sticks as a molecule on the surface of the solid material. There is absorption, the hydrogen splits into atoms. That atom goes and sits in the interstitial space of the molecule. So the examples are metal hydrates and complex metal hydrates. So metal hydrates where hydrogen forms a single bond. In case of complex metal hydrates, hydrogen forms a complex bond, more than one bond. So we are going to discuss more about metal hydrates in this talk because they are proven to be cyclable, reversible, stable, for few thousand cycles. Whereas complex metal hydrates are not at inside to reversible, because if you take, for example, complex metal hydrates, if you take alanates, borates, they release good amount of hydrogen, gravimetrically. If you take 100 kgs of material, they show up to 10% of hydrogen they can store in that. But they are not inside to regenerate. They won't absorb immediately hydrogen. The cyclability is still a question. Of course, a lot of research has been happening for last 30 years. Many ways the researcher has tried to make these reversible, but not yet successful, because they have high hydrogen storage capacity per unit mass when compared to the metal hydrates, but still the challenge is recyclability. Sorry. So if you take metal hydrates, as I told, they are reversible. They absorb hydrogen and dissolve hydrogen reversibly for a few thousand cycles. So that's why they found applications, because they can be used repeatedly for a few thousand cycles. So they have a lifetime. They can be used for a few years once we start putting them in use. So these metal hydrates are of three types. Generally, we can characterize based on the temperature at which they absorb and dissolve hydrogen. If they dissolve hydrogen less than 50 degrees centigrade, we call them low temperature metal hydrates, because they can readily dissolve hydrogen at near atmospheric conditions. Or we may need to increase their temperature between 100 and 300 degrees centigrade. So they are called medium temperature hydrates. And some hydrates only dissolve hydrogen at very high temperatures of the order of more than 300 and 350 degrees centigrade, like magnesium. Okay, so these are all called high temperature applications. So each has certain applications. Suppose if you see for hydrogen for mobile applications, you generally look for the materials which can store readily at near atmospheric conditions, because you don't want to use high temperatures for their absorption desorption purpose. Okay. So the tanks looks like this. It is a kind of a shell and tube kind of heat exchangers, which can be staggered into a unit. So those can be used along with the cars. Okay. So if you compare the three methods of hydrogen storage, the first one we have discussed is compressed hydrogen storage. The second one is liquefied hydrogen storage. And the third one is a solid state hydrogen storage. So all the three has their own advantages, disadvantages. So if you see the three technologies, compressed hydrogen, here I am showing it only 200 bar. If you go up to 800 bar, the size of the tank further reduces. Liquid hydrogen, and then gaseous hydrogen, solid state storage of hydrogen in room temperature materials, which has lesser gravimetric hydrogen storage capacity. That means if you take lanthanum, it only stores 2% of hydrogen per unit weight. If you take 100 kgs of lanthanum nickel 5, it can store only 2 kgs of hydrogen. Whereas if you take magnesium based hydrates, but they operate at high temperatures, they can store up to 6 to 7% of weight. That means if you take 100 kgs of material, it can take 6 kgs of hydrogen. Okay, so the volume reduces as the per unit mass. If you can store more amount of hydrogen, of course the volume reduces. This is a comparison of different volumes when you're storing hydrogen, compressed hydrogen at 200 bar, liquid hydrogen at 20 Kelvin, and then hydrogen in solid state with the two different gravimetric energy storage, hydrogen storage capacities. One is 2 weight percentage and the second one is 6 weight percentage. So as we see, the volume will be lesser in case of the solid state. But the challenge associated with solid state hydrogen storage is the gravimetric density, because they will become heavier. Okay, because they can store less amount of hydrogen per unit mass in solid state, the metal hydrides. So they require they weigh a lot for storing the same amount of hydrogen. So here two parameters are very important. That means the amount of hydrogen that can be stored per unit mass of the storage unit and per unit volume. Okay. Of course, per unit volume, it increasing from gas to liquid and liquid to solid. But whereas per unit mass, the solid has less hydrogen storage capacity. Hence, for carrying the same amount of hydrogen, it heaviers more. It becomes more and more heavy. Okay. But nevertheless, these materials, metal hydrides, find many stationary applications for hydrogen storage. We'll see some of the stationary applications. I'm going to highlight three types of stationary applications. So before going into study how these metal hydrides are used for storing hydrogen for stationary applications, let us see brief chemistry about the hydrogen absorption, desorption of metal hydrides. So if you take a metal matrix, it is commonly a metallic, intermetallic or an alloy. No, it is an intermetallic or an alloy. It shows the solid matrix. So hydrogen, when you send hydrogen over this solid matrix, initially it sticks over the surface of the solid matrix. So when the pressure increases over the surface at a certain pressure, the hydrogen gets dissociated into atoms that goes and sits into the interstitial space of the solid matrix. Because if you take any solid, we have molecules. The molecule is made up of a lattice. We know different lattice structures like face-centered cubic or hexagonal HCC structures like this. So atoms are arranged in a particular fashion and there is a gap between the atoms. So this hydrogen goes and sits in between the atoms, within that lattice structure, between the gap of the atoms. So once the hydrogen atoms gets filled into the lattice, again the hydrogen starts filling over the surface. So this hydrogen absorption is a exothermic reaction. That means when metal is transforming into metal hydride, it releases heat. And similarly, when you want to drive out the hydrogen, you have to supply heat to it. Okay. So in a hydrogen absorption desorption cycle, we have two heat interactions. So while absorbing hydrogen, it is an exothermic reaction and heat is released. For desorbing hydrogen, it is an endothermic reaction. We have to supply heat. Okay. So in one complete cycle, we have one heat absorption desorption cycle also. So these heat release or heat supply during hydrogen absorption desorption can be effectively used for building some engineering devices. For example, we can compress the hydrogen thermally from low pressure to high pressure, or we can develop sorption based cooling and heating systems, like at least the mechanical engineers study in refrigeration and air conditioning the ammonia water system or lithium bromide water system, where using the heat energy, we produce the cooling effect. Okay, so that is sorption cooling systems, we call absorption cooling systems, we say that. Okay, and this the heat interactions during hydrogen absorption and desorption can also be used for energy storage, thermal energy storage. Of course, there is one more application, nickel metal hydride batteries. So this is one of the commercialized application, but nevertheless, because of lithium-ion batteries, they have higher energy storage density and longer cyclability. So these faded away slowly in the nickel metal hydride batteries. And we can purify hydrogen also. Suppose we are producing hydrogen from fossil fuels, we find the traces of carbon dioxide, carbon monoxide, water, other gases. So by selectively absorbing and desorbing hydrogen, the metal hydrides can also be used for purifying the hydrogen or to remove the impurities in the hydrogen. Okay. So to select any material for a particular application, we require thermodynamic properties. We start with any selection of any material with the help of the thermodynamic properties also. So here also we require certain thermodynamic properties to understand how these energy conversion systems work. So one of them is the pressure concentration isotherms. That this is because we have the metal phase, metal hydride phase, and the pressure and temperature concentration. All the three are the three thermodynamic variables. So this shows at a particular temperature, if you are increasing the pressure of hydrogen over the solid material, how the concentration is varying in the material. That means how it is being going into the being absorbed. Okay. So this shows a particular isotherm, that means a constant temperature curve, when the pressure is being increased over the surface of the solid material. For example, if you take earlier slide, you take a solid material, this solid material in a container, that is metal hydride in a container, and you start supplying hydrogen. Initially, there is no hydrogen. Okay, so the pressure is there is no pressure, maybe atmospheric. Then you start supplying hydrogen. What happens when you start supplying hydrogen? The hydrogen starts accumulating over the surface. This is accumulating over the surface of the solid. So at a particular pressure, when it reaches a particular pressure, break-even pressure, then the hydrogen metal hydride formation starts. Okay, the hydrogen molecule gets dissociated into atoms, and that goes into the interstitial space of the solid, forming the metal hydride. So this is from this point to this point, it is the formation of the metal hydride. So once this space is filled, the lattice space is filled, again the hydrogen starts accumulating over the surface, forming a beta phase. It is again a solid solution. Okay, so the metal hydride formation is from here to here. So this is at a particular temperature. There is a pressure at which this metal hydride formation or dissociation takes place. So what happens when when we increase the temperature of the solid material, the pressure at which this formation happens also increases. Or when we reduce the temperature, the pressure at which the formation happens also reduces. This is similar to your pure substances. Especially in thermodynamics, we study the properties of pure substances. There we study that there is a temperature corresponding to each pressure. There is a temperature at which a pure substance undergoes a phase change from liquid to vapor. Generally, we study. That's more interesting. So there, if you take a TV diagram, we see that the pressure, the temperature increases for an isobar, and then it remains constant till the entire fluid gets converted from liquid to vapor state. This is very similar to that. Okay. So this data, what it tells is, if you know the temperature, you know the pressure at which the metal hydride forms, or if you know the pressure, you know the temperature at which the metal hydride forms. These two are fixed. Okay, thermodynamically at least they are fixed. So this P and T relation can also be used to plot the Van 't Hoff equation, which is very similar to the Classes-Capitan equation, where you can find out what is the amount of hydrogen released during what is the amount of heat released during the hydrogen absorption, or what is the amount of heat that you need to supply for a dissociation of the hydrogen. Okay, so this forms a very important information for selecting the materials for energy conversion applications. So let us see with an example how we can use this knowledge of the dependency of metal hydride formation on pressure and temperature. Of course, each two are dependent variable. Once you fix the pressure, the temperature at which the formation takes place is fixed, or once you fix the temperature, the pressure is fixed. Okay, so if you see, these are the isotherms drawn. This is like a phase change process where this shows where we completely connect all metallic points. So from the metal, it transforms into metal hydride. So here at this point, it has become metal hydride complete. So this point, this line which shows the saturated liquid line in the properties of pure substance, it shows a kind of the point where the metal hydride formation takes place. That means till to the left, it is completely metal. Here it has completely become a metal hydride. Here the second solid phase is taking place. So corresponding to each temperature, the pressure, there is a pressure where this is happening, that is increasing with increase in temperature. So exactly this logic we use to compress hydrogen thermally. So what we do is, we take metal hydride in a reactor, we keep it at room temperature or a lower temperature. Okay, initially by circulating a fluid through the bed. Of course, the the fluid and metal hydride won't be directly in contact. There will be kind of a shell and tube arrangement where shell side you have metal hydride and tube side the fluid is being circulated. So the fluid is circulated at a lower temperature, maybe the room temperature or atmospheric temperature. So the metal hydride formation happens at a lower pressure. Okay. So when it gets saturated with the hydrogen, now what I do is, instead of supplying the fluid at a lower temperature, I supply the fluid at a higher temperature. Suppose I supply water nearer to 100 degrees centigrade, almost steam. Okay. So what happens? I am just heating the bed from room temperature to the higher temperature. Let us say here T4 in this diagram. This is the T4. So now what I do is I just open the wall, so that what happens? The hydrogen is coming out at a high pressure. So I can store hydrogen at a much higher pressure. If you compare the P and T relation of different metal hydrides, you can see that, the pressure is varying from with variation in temperature. The pressure is for each hydride, the pressure is varying almost up to 1000 degrees centigrade for certain metal hydrides. So that means you can absorb it at a low pressure when the temperature is low. This is 1 by T, okay, not T, 1 by T. At a low temperature, you can absorb it at a low pressure. When you heat it to a high temperature, okay, then you can get desorption at a high pressure. Okay. So this way we can reduce the amount of energy and the quality of energy required for compression, especially in mechanical compressors, because we use lubricants. The hydrogen can also mix up with the lubricant. Okay, so here we can avoid all these problems. Okay, we are using a low grade energy as the energy input. There is no vibration free. It is only changing the temperature of the bed by circulating the fluids at two different temperatures, and there is no scope for leakage and no lubrication required. And this can also act as a compressor as well as purifier, because while absorbing metal hydride absorbs only hydrogen. Any impurity gases we can send it out. While desorbing it, it releases very high pure hydrogen. So it can also be used as compressor plus purifier. Okay, any traces of water or oxygen is there, even in electrolytic process, we can remove them. Okay, and we can compress it to very high pressures. So the other application is, the sorption based cooling systems. So as I told, metal hydride requires energy for desorbing hydrogen. Suppose let us say I have a metal hydride bed B, where A and B are two metal hydride beds I have. In metal hydride B, I have filled this mish metal based hydride, MmNi 4.15, Fe 0.85. So this is desorbing hydrogen, let us say at near to 3 or 4 bar. Okay, this desorbing hydrogen, because it is desorbing hydrogen at 0 degrees centigrade, it requires energy. It collects heat from the surroundings. So that means the surroundings, it can cool up to 0 degrees centigrade. So we are producing the refrigeration effect. We are absorbing heat less than atmospheric temperature. Okay, near to 0 degrees centigrade we can absorb. This is an example only. We can go up with using alloys, we can go up to -50, -60 degrees centigrade also by choosing the proper metal hydride for B. Okay, so in this example, it is desorbing hydrogen at 0 degrees centigrade by absorbing heat from the surroundings at 0 degrees centigrade. That means we are producing the refrigeration effect. Of course, this dissolved hydrogen by metal hydride bed B is absorbed by metal hydride A. So that is lanthanum based hydride in this example. So this is absorbing hydrogen at 40 degrees centigrade. That means it has low pressure compared to this material. These two materials has two different P and T relation. Okay, so the pressure, this is a low pressure alloy, this is a high pressure alloy. So this, even at 40 degrees centigrade, it has a low pressure plateau, so it can absorb at a low pressure. So it, while absorbing hydrogen, it is rejecting heat at 40 degrees centigrade to the environment. Now the refrigeration effect is over once the hydrogen gets transformed. So we have to continuously produce the refrigeration. We have to drive back the hydrogen to this original bed, the initial bed. How we can do it? We have to heat this bed to a high temperature. Here it is shown as 180 degrees centigrade. The lanthanum based hydride, which initially absorbed hydrogen at 40 degrees centigrade, has been heated now to 180 degrees centigrade. Whereas the other alloy I am heating it to 40 degrees centigrade, this alloy, the metal hydride B, which is responsible for refrigeration effect. So now, because this is releasing at 180 degrees centigrade at a high pressure, that can be absorbed by the metal hydride B, that is mish metal based alloy at 40 degrees centigrade by rejecting heat to the environment. Okay, so in a refrigerator, any refrigerator also we have to reject heat to the environment, which we generally keep 45 or 50 degrees centigrade. So we can keep here even at 50 degrees centigrade. That's not a problem. So now hydrogen has come back to this metal hydride bed B. Now we have to cool both the beds to the initial temperature so that we can continuously operate this in a cycle. So this is thermodynamically shown here. So refrigeration temperature, this is 1 by T again, this is 0, this is 40, and this is 150. So initially hydrogen being transferred from metal hydride B to metal hydride A. This is hydrogen transfer. So it is absorbing heat at 0 degrees centigrade. Then it is heated to 40 degrees centigrade, whereas this bed is heated to 140 degrees centigrade. Now hydrogen is coming back to the initial bed. Okay, so it is like a closed thermodynamic cycle where we can use the thermal energy to continuously produce the refrigeration effect. Okay? So we have demonstrated this using lanthanum based hydrates. So we need one high pressure alloy here. If in this example, mish metal nickel 4.15 Fe 0.85 is a high pressure alloy, and whereas the lanthanum based hydride is a low pressure alloy. Okay, so using this we can just a second now. So using this one high pressure alloy and one low pressure alloy, we can construct a closed loop thermodynamic cycle where we can continuously transform the heat energy, which is here in this case, into a refrigeration effect. So we have taken lanthanum LaNFi, which is generally has a plateau pressure of 2 to 3 bar. So if you substitute, you can substitute other elements for lanthanum and nickel, other radioactive elements for lanthanum, or aluminum, manganese, cobalt kind of elements for nickel, and you can alter their plateau pressures. For example, in this case, we substituted cerium for lanthanum. Okay, so that its plateau pressure, the pressure at which it absorbs hydrogen, has increased with substitution of cerium, so it becomes a high pressure alloy. When I substitute aluminum for nickel, it becomes a low pressure alloy. It means it can absorb and dissolve hydrogen at a low pressure. Okay, so I'm able to produce one pair of high pressure alloys and one pair of low pressure alloys. Of course, this is not easy process to obtain these intermetallics or alloys, because all the elements has different melting points. If you take lanthanum, nickel, aluminum, lanthanum has a melting point of about 800 degrees centigrade, 800 to 900 degrees centigrade, depending upon the source. Nickel has maybe around 1400, and aluminum has 600 degrees centigrade. Very difficult to produce these intermetallics. So you require special melting knowledge to obtain these intermetallics. So once you have the intermetallics, you need to test the pressure concentration isotherms really, whether you are getting the required properties or not. So we have developed a setup indigenously. This is called Sievert apparatus to measure the isotherms. So to measure the isotherms, the material is taken in a reactor, which is kept at a constant temperature. This is initially evacuated. The material is evacuated, so there is no hydrogen. Then hydrogen is supplied to this material in steps from a known volume. So this volume is calibrated, and hydrogen is in the first step, it is supplied from vacuum to maybe 1 bar, so that hydrogen gets being absorbed, and we can quantify the amount of hydrogen absorbed by using the mass balance. So we'll get 1 point at a constant temperature. Then we step up the pressure and we get the second point. Like that, we can plot a series of points. Okay, so we'll get isotherms like this. Of course, this should be thermodynamically, theoretically, it should be flat, but because of the inhomogeneity in the materials, it shows a little bit slope. This plateau shows a slope. So we have measured the isotherms of cerium-based hydrates, 2 cerium-based hydrates, and 2 aluminum-based hydrates. Basically, aluminum-based hydrates are low-pressure hydrates, and cerium-based hydrates are high-pressure hydrates. So we make combination of 1 low pressure and 1 high pressure. We can make 4 combinations. So these work in a closed loop, as I told, with the temperature swing, the hydrogen being transformed between the 2 beds. So there simultaneously we can use the heat energy to produce the cooling effect. So here we have tested it at 25 degrees centigrade heat rejection, 140 degrees heat supply, and 10 degrees for the refrigeration effect. So 10 degrees refrigeration can be used for air conditioning applications. So we have tested all the 4 alloys, and thermodynamically we have seen that we can obtain a COP of 0.8, which is comparable with the lithium bromide water systems theoretically, but it is only a kind of a thermodynamic limit. If you take actual heat and mass transfer where it involves a lot of irreversibilities, the performance may come up to 50% of that. Maybe we can obtain for 0.4, 0.5 COP with these metal hydrides, but the advantage with these systems is you can go very low temperatures, you can obtain very instantaneous cooling, fast blasting cooling. You can obtain -50, -60 also very fast, which is very necessary for your food processing applications. And a variety of energy source temperatures can be used. And as I told, metal hydride compressor also, we have tested a kind of a metal hydride compressor. We have built a metal hydride reactor and tested using cerium based hydrates. Earlier we have shown the cerium based hydrate, and it means theoretically you can absorb at 20 degrees centigrade, you can absorb hydrogen at 5 bar. When you heat the bed to 80 degrees centigrade, you are going to dissolve hydrogen at 40 bar. You can obtain a pressure ratio of 8 just by using heating water at 280 degrees centigrade. So this is the experimental setup we have built to study the hydrogen. This is one of the DST funded project. We have developed an experimental setup to experimentally test the performance of the metal hydride reactor for hydrogen absorption, desorption, thereby the compressing the hydrogen. So what we do is we supply this coolant at water at, this is a thermostatic bath which can supply water at a constant temperature. So we supplied water at room temperature initially and absorbed hydrogen in this metal hydride bed. This is the metal hydride bed which is shown here. So centrally the water is supplied at the periphery, and metal hydride occupies this, and hydrogen is supplied centrally. Okay, so it gets hydrogen. Metal hydride absorbs hydrogen from these cylinders. So while dissolving, we dissolved into another cylinder. Okay, and at a high pressure. So we can get hydrogen from a low pressure to high pressure by operating through metal hydride using the thermal energy. So this shows the reactor that was used for the hydrogen compression studies. So we have studied 3 types of beds for hydrogen compression. One is powder bed, because powder bed, what happens, it is the particles are loosely packed. The heat transfer will be not that much good in case of the powder beds because of the lower effective thermal conductivity of the metal hydride bed. So to increase the heat transfer characteristics, we have made some pellets kind of things. Okay, so we have made 2 types of pellets. One pellet just by mixing the metal hydride and graphite powder, which is having higher thermal conductivity. So that when we compact it, what happens is the conductivity becomes more, but there is a problem with the diffusivity. So if you use higher pressures, the compact becomes very tough. Then the initial diffusion may get affected because the hydrogen has to diffuse through the solid particles. And we also use this aluminum mesh. These are all porous aluminum wires, plates made into mesh kind of fins to enhance the thermal conductivity. So we have tested the hydrogen desorption rates for these 3 beds, because the hydrogen absorption and desorption rates gives the time which is required for decides the cycle, how fast you can do the compression process. Okay, if it is hydrogen absorption and desorption is faster, then you can obtain in a less time, you can obtain a compressed hydrogen. Okay, so the compacting has definitely increased the heat transfer characteristics, thereby the hydrogen absorption and desorption rates. Okay. The other application is storing the heat energy. So when you have this high temperature heat, you can supply to the metal hydride bed. So the hydrogen comes and stored in a cylinder. So that means you are storing energy by dissociating to one metal hydride into 2 elements, hydrogen and material, that is metal. So when you want this heat energy to be retrieved, you can supply hydrogen back to this, so that you can circulate a low temperature fluid at the inlet, so it comes out as a high temperature fluid. Okay, so you know that the hydrogen energy storage can be done, thermal energy can be stored by sensible heat storage, latent heat storage, and thermochemical heat storage. So the energy storage density increases from sensible to latent heat and to the thermochemical energy storage. The other advantages with thermochemical energy storage is you can store for any amount of time the thermal energy without losing its exergy, because once you start the hydrogen being absorbed by the metal hydride, it dissolves the same amount of heat at almost similar temperature. Okay, and it has higher volumetric energy density. So if you see the advantages, why metal hydrides? So these can be operated for a longer duration, few thousand cycles. So once you build the system, it is operatable up to 30 years of life. It has very high energy density, a larger temperature ranges, temperature range heat sources can be used for energy storage, maybe from room temperature to as high as 550 degrees centigrade. Energy sources can be, the energy can be stored at different temperatures. Okay, so what are the requirements of metal hydride? It should have faster kinetics, a higher hydrogen absorption desorption rate, higher heat of reaction, so that you can store more amount of energy for a given material size, and the cost of these materials should be less. It should be cyclically stable, and it should have good hydrogen storage capacity. So especially when you see the concentrated solar power plants, you require a temperature of the range of 300 to 500 degrees centigrade. So there magnesium is found to be a good material for storing the thermal energy. So because magnesium also releases a lot of thermal energy per mole of hydrogen. But it is the kinetics, the hydrogen absorption desorption rates of the pure magnesium is less. So it has to be made some kind of intermediate, the composites has to be made. For example, magnesium can be altered, the properties can be altered by making the intermetallics or alloys with nickel or aluminum, or we can mill the magnesium with other metal hydrides to make the composites, or it can be added some catalysts to make composites. So these are tested for, using a kind of a reactor like this. These are tested for energy storage using this setup, which was built at IIT Madras by one of my colleagues. And it was proven that, if you see, if the absorption starts at 150 degrees centigrade, so the temperature of the metal hydride goes up to 450, 400 degrees centigrade nearly. So that means you can recover the energy at almost at 400 degrees centigrade by supplying hydrogen at a high pressure. So here, not only the energy storage at higher temperatures is possible, but it can also be recovered at a higher temperature than what it is stored. It is called heat transformation. Okay, so you suppose you have a heat source at 300 degrees centigrade, you are storing heat energy at 300 degrees centigrade. You can recover it at much higher, maybe even 450, 500 degrees centigrade is possible. So this is one of the important applications of this hydrogen absorption and desorption. So ultimately, it comes to what is important while designing the metal hydride beds is, as an engineer, mechanical engineer, we look at the design of the beds. So there the heat and mass transfer plays a very important role. So the heat transfer is mainly governed by the effective thermal conductivity of the beds. As I told, the effective thermal conductivity is nothing but the heat conducted through the solid material in the bed, the gas and solid interaction. So there are several techniques to measure the effective thermal conductivity. So we have used one of the steady axial one-dimensional heat transfer technique to quantify the metal hydride bed thermal conductivity. Of course, this thermal conductivity varies with the hydrogen concentration, pressure, and temperature of the bed, because as the hydrogen goes into the interstitial space, the molecule swells. Because of that, the contact resistance between the molecules reduces, thereby the conductivity increases. So we have done the tests to three types of beds, again, the powder bed and the two pellets, what I have shown earlier. So the pelleting has significantly increased the effective thermal conductivity. Otherwise, the bed has lower thermal conductivity. So here, not only the conductivity, the other parameters also plays the heat and mass transfer characteristics of the bed. So this is also one of the important research problem where you need to optimize the heat and mass transfer characteristics of these solid reactive beds. Okay. So the heat transfer can be done either through gas cooled or gas heated or liquid cooled and liquid heated. So these studies are very important. This is one of the study conducted by colleague at IIT Madras. So he has taken different configurations, proposed different kinds of metal hydrate beds. So here in this case, for example, you have a shell kind of reactor where the material is placed throughout the shell, and the bigger circle shows the through which the coolant is supplied, and the smaller dotted shows the through which hydrogen is supplied. So this is liquid cooled or liquid heated metal hydrate bed. So these two shows the gas cooled or gas heated with a different fin configuration. So these need to be solved to study the variation of the concentration of the hydrogen within the bed and the temperature of the bed as the hydrogen is being absorbed and dissolved. So for that, a unit cell is considered, and COMSOL multiphysics is used, because here we have to do the mass balance and energy balance, as well as the diffusion reaction we have to solve. So all these three reactions are solved simultaneously using this solver, COMSOL solver. So let me see whether this is working or not. No, sorry, it is not working. So what happens is we can see this through the simulations how the temperature and concentration of the bed is varying. If you see, for example, with the time, it gets transformed from blue to red as it becomes from metal to metal hydrate. So the challenge is how to arrange this overall configuration, how to reduce the size as well as the weight of the reactor. So the optimization need to be done with respect to these parameters to reduce the size and the weight of the metal hydrate devices. Okay. So with this kind of research, we of course the material development is very important. We will able to develop the devices, especially for solid state hydrogen storage. So in the nutshell, if you see, we have three options. One is compressed hydrogen, where we need to develop type 4 cylinders and efficient hydrogen compression technologies. The second one is liquid storage, where we need to work on technologies to obtain lower temperatures for liquefying the hydrogen and storing it efficiently with better insulations without losing much hydrogen due to boil-off losses. The third one is solid state hydrogen, developing materials with high gravimetric energy storage density and designing these devices effectively for faster hydrogen absorption and desorption rates. So in the future, if we can develop all these technologies, the energy spectrum is going to look sustainable like this. We use the renewables or nuclear energy or carbon-free fossil fuels to produce hydrogen. While doing it, we take water from the environment and release oxygen to the environment. And when we use hydrogen for applications, we may combust or use along with the fuel cells and release water into the environment and take oxygen. It is a kind of a sustainable circle. This also be combined with the electricity. Okay, we use hydrogen and electricity parallelly for using the intermittent renewable energy sources to effectively integrate with the users. So this is also a kind of a sustainable model where we are integrating the intermittent sources for effective utilization with the users using the hydrogen and as well as electricity as two energy carrying vectors. Okay, so I think I'm coming nearer to the end of my talk because the given time, another 5 to 6 minutes is left. I'll show a small video on a lighter note for the viewers to have a happy ending. Then I'll take some questions based on my talk. Sorry. Yeah, thank you. Thanks for your patience.
So thank you so much, sir. Is there any questions from audience side? You please raise your hand so that sir will uh, so there is a one question in chat box, sir. If GFRPs are used for hydrogen storage, if they are to be welded or jointed, how they can be joined, sir?
You mean to say this composite materials? What I did not get. What is GFRP?
Dear Krishna Varma
I think
Garu,
it's a glass fiber related,
Okay,
sir.
okay. Maybe some composite he's talking about. Yeah, I'm not. I don't know the complete manufacturing process, but yes, it is challenging because it is not only there are intricate shapes. In manufacturing, there is a challenging process. Whether really welding is being used there or not, I'm not sure.
Sir, one question from my side. I mean, actually, it is doubts and not question. Sorry.
Yeah.
Activated carbon plays a vital role. I mean, it's a key role in the hydrogen production, no, sir.
Production
I mean, hydrogen production point of view, activated
using electrolyzers.
using electrolyzers typically, but if I choose any biomass pyrolysis process or a gasification process,
Yeah.
in that process, same metal hydride type reactors can be employed, or we have
No,
to.
metal hydride is completely different reactor. It is a kind of a reactive packed bed kind of things. Okay, so there the pyrolysis and all require different kind of reactors.
Oh, these reactors cannot be used to produce.
No. These are all for storing. These are all. It's a kind of mixture of mechanical and chemical. Thermochemical where
Yes, sir.
it is a kind of a heat exchanger design.
Okay. So that means if in case of pyrolysis process, hydrogen production also there, no, sorry, means
Yeah, definitely it is there, but it requires a different kind of reactor there.
it's okay.
Yeah.
Any other questions? So there is a one question, sir. How can hydrogen be kept in flammable limits during storage?
See, generally, if you are using solid state, what happens is while hydrogen is being released, the temperature of the bed automatically comes down because of the endothermic nature. Okay, so it is a safer method. And when you're using liquid, of course, it is much lower temperature. It is in the flammability range. And you are using compressed also, generally the temperature will be room temperature only. It won't be higher temperatures while storing. So I don't think any problem will be there during the storage with respect to flammability. Yes, if there is a hydrogen leakage and the environment gets exposed to a higher temperature, then only there is a possibility of ignition of this mixture.
I hope it is clear. So is there any other questions? Anyone else?
I think no other. See one more question from the chat box.
Yeah, there is a question. What are the recent trends of hydrogen storage in terms of material characterization level? Yeah, people are still studying a lot of materials because these heavier metal hydrides are generally heavy. They have lesser gravimetric storage capacity. So the recent trends are more towards, of course, complex metal hydrides are also enough thoroughly studied. Now people are thinking of using some solid matrix at medium temperatures, not cryo, not 20 Kelvin, using metal organic frameworks, for example, Okay, they give very high hydrogen storage density at 77 Kelvin or 150 Kelvin. This is a kind of an intermediate method. Or if you can store it in liquid stage within inside to reformer, okay, like methanol and all, that is going to be a better solution. But to me, in the next 4 to 5 years, I don't think any material revolution may come. So generally, the compressed hydrogen may be used for transportation application, whether it is a ship transportation or train or or even vehicular applications. Of course, solid state can be used for two-wheeler and three-wheeler at current, even using metal hydrides. It's demonstrated at IIT There was earlier one three-wheeler which runs on the solid state hydrogen storage. Of course, scooters are developed everywhere, and this fork vehicles, that four-wheeler, that is also being demonstrated using hydrogen and fuel cell at many places.
So Dr.
Yeah, how
Naresh,
can we study the charge and discharge cycles of absorbed to hydrogen storage on activated carbon? Yeah, we have to measure the kinetics for this. Okay. There are instruments for measuring the kinetics. Using the kinetics measurement, we can estimate the rate of hydrogen absorption and desorption on the activated carbon. There are a lot of papers on this.
there is a question, sir. What is the commercial status of solid state hydrogen storage?
Yeah, solid state commercial we have not reached to the commercial stage. It is still a nascent technology only. We are trying to develop some modular applications using the solid state, not for transportation applications. Okay. So we may need to have a small tank of where we fill hydrogen and use for modular application. Shall we use fluidized bed reactor instead of fixed bed reactor? No, I have not seen this because fluidized bed means it's a completely different concept, because here the hydrogen is going into the solid, so unless otherwise you have complete packed solid, you may not get a higher storage capacity when you are hydrogen being absorbed by it.
So I hope everyone is clear, so that we can stop the session. So on behalf of all of the participants, I would like to extend our heartfelt thanks to our esteemed resource person for delivering an excellent session on hydrogen storage technology. Your insightful presentation covered a wide range of topics, including advanced storage methods such as compressed gas, liquid hydrogen, and metal hydride, providing us with a true understanding of this crucial aspect of hydrogen value chain. The practical application, challenges, and future possibilities you shared have been truly enlightening and have sparked new ideas for innovations in the field. This session has added immense value to our knowledge and research pursuits in sustainable energy. Thank you once again for your time, expertise, and thoughtful discussion. We hope to have a privilege of learning from you again in the future. Thank you, sir.
Yeah, thank you very much. Thank you, all of you. Thanks to the organizers for giving me this opportunity, and thanks to the listeners, audience, for patient listening for 1.5 hours at odd hours. Okay, I wish you all the best in your research careers. Thank you very much.
Thank you, sir. Thank you. Thank you on behalf of everyone present here. I extend our heartfelt thanks to you for providing such an insightful session on hydrogen storage technologies.
Yeah, we are in time, I think. Just exceeded 5 minutes. Anyway,
No,
yeah,
sir, actually, most of the
Thank you,
audience
sir.
are eagerly
Thank you once
waiting for
again,
your
sir, for
presentation.
enlightening us.
No, sorry, I rushed through some slides at the end because of the time constraint. Yeah. Yeah, thank you.
Thank you, sir.
Thank you, sir. So, sir, please hold for a few seconds, sir.
Yeah, sure.
So, dear participants, can you switch on your video so that we can take a snapshot with our esteemed guest, Anil Kumar Garu? Hold for 5 seconds, sir. Yes, sir. My job is done. So, you can sign up the session, sir. Thank you
Yeah,
so much,
thank you,
sir.
thank you, thank you.
Thank you, sir. Dr.
Yeah,
Ravi.
dear participants, we'll share that presentation in the WhatsApp group, and all the sessions will post it in that WhatsApp group. And one more thing, so as of now, I hope everyone is learned. You got some insightful, fruitful information from the experts. So tomorrow we have three more sessions like that, so that our after that our FDP program will be successfully ended up. So I hope uh, I hope please join early. Tomorrow actually it will be early. From afternoon tomorrow 2 o'clock onwards the sessions will be begin. So please join as early as possible. And after that, after the sessions will be over, we are going to take a feedback from your side, and in orally and as well as documented way. And apart from that, we are going to conduct one session. All the sessions, we are going to take some test also. So that test will be, it is crucial. We'll share that Google form, the test-based Google form we will share with you. So you please respond in the test. After that, this testing is over, then evaluation will be done so that you can generate the e-certificate. So I hope everything is clear. So if you have any queries, please feel free to ask us. So testing time will be like it is from 6:30 onwards, sir.
Dr. Ravi, kindly share the timings also. From first session is from 2 to 3:30. So I think second session is 3:30 to 5. Third session is 5 to 6:30. And
Yes.
then after these three sessions, 6:30 to 7:30 is feedback and online test. And then 7:30 to 8 is the valedictory function. I hope
Yeah, it
everything
is objective type questions only. So we'll give 20 questions. So all are multiple choice questions only. So the test is not that much complicated. It is simple only. It is depends on that sessions as of now how the sessions it is based on sessions how we are handling. So based on that only the test will be going on.
Okay, concluded.
Okay. So I hope everything is clear. So that please be there tomorrow 2 p.m. onwards. So that we'll have a three more fruitful sessions will be there. So after that, after testing is over, test session is over, then we can have a validator session. After that, we can end up this FDP program with successfully. Thank you so much for your kind cooperation. Thank you so much, sir.
Thank you. I'm closing the session. Thank you, Nadal. Have a good day, everyone. Thank you.